Right now, a single beam of light leaving our sun takes 8 minutes and 20 seconds to reach the surface of Earth. That same beam continuing outward past our planet, past the outer planets, past the frozen debris at the edge of our solar system, would travel for 4 years and 3 months before it finally brushed against the atmosphere of the nearest world orbiting another star. 4 years, at the fastest speed the universe permits, at a velocity so extreme that in the time it took you to read this sentence, that beam crossed a distance greater than the circumference of our entire planet 7 times over. And yet 4 years at the speed of light translates to something far more devastating when measured against the fastest machine humanity has ever built. The Parker Solar Probe, launched in August of 2018, represents the absolute pinnacle of human engineering achievement in the domain of velocity. During its closest approaches to the Sun, this spacecraft reaches speeds exceeding 430,000 miles per hour. At this velocity, you could travel from New York to Los Angeles in under 20 seconds. You could circle the entire equator of the Earth in just under 4 minutes. The probe moves so fast that no human could survive aboard it, not because speed itself is fatal, but because the trajectory that produces these velocities carries the spacecraft close enough to the Sun to experience temperatures that would vaporize steel. This is the fastest we have ever gone, the fastest any object built by human hands has ever moved through space. At 430,000 miles per hour, the journey to Proxima Centauri, our nearest stellar neighbor, the closest sun to our own, would require approximately 6,600 years. 6,600 years ago, the wheel had not yet been invented. Writing did not exist. The pyramids of Giza would not be constructed for another 1,000 years. A spacecraft departing Earth at humanity's current maximum velocity, when the first cities of Mesopotamia were being laid out in river clay, would only now be approaching the first star beyond our own. But here is what most people misunderstand when they encounter this number. The problem is not merely one of engineering. It is not simply that our rockets are too slow and that smarter engineers will eventually solve the equation. The problem runs deeper than that, far deeper. It reaches into the fundamental structure of the universe itself, into the physics of motion and mass and energy, into laws so absolute that no civilization anywhere in the cosmos can escape them. And yet, within those same unbreakable laws, there exists a loophole so profound, so counterintuitive, so deeply woven into the fabric of space-time that it transforms everything we think we know about distance, time, and the limits of a single human life. A loophole discovered not in a laboratory, not by a team of engineers with access to the world's most powerful instruments, but by a 26-year-old man sitting at a desk in a patent office in Bern, Switzerland, asking a question so simple that it sounds almost childish. What would it look like to ride alongside a beam of light? The answer to that question, it turns out, does not merely change how we think about space travel, it changes what space travel fundamentally means. It reveals that the universe has not designed an impenetrable wall between humanity and the stars. It has designed something stranger, something more generous, and something that demands a price so personal that the mathematics alone cannot capture what it truly costs. If journeys like this one, through the physics of motion, through the machinery of time, through the outer edges of everything reachable, are the kind of content that moves you, then please consider hitting that like button and subscribing to this channel. It takes only a moment, and it genuinely helps this work reach further into the world. Every subscription is another person who might one day look up at the night sky and truly understand what they are looking at. Make yourself comfortable. This will take a while, and it will be worth it. Let's begin. To understand why the speed barrier matters so profoundly, you must first understand what speed means across cosmic distances. Not speed as we experience it on Earth, not the sensation of acceleration pressing you into a seat, not the blur of landscape outside a car window, but speed as a ratio against the only velocity that the universe treats as absolute. The speed of light in a vacuum is 186,282 miles per second. This number is not merely fast. It is as far as every experiment and observation in the history of physics has determined the maximum speed at which any information, any signal, any particle, any object possessing mass can travel through space. It is not an engineering ceiling awaiting a more powerful engine. It is a structural feature of reality, as fundamental as the number of spatial dimensions we inhabit. At this speed, light crosses the distance from Earth to the Moon in approximately 1.3 seconds. It reaches Mars at its closest approach to Earth in roughly 3 minutes. It takes 8 minutes and 20 seconds to travel from the surface of the Sun to our planet, and it requires 4 years and 3 months to reach the nearest star. These numbers reveal the first and most important truth about interstellar distances. They are not merely large. They are large in a way that makes all human experience of largeness completely irrelevant as a reference point. The distance from New York to Los Angeles is large. The distance across the continental United States is large in a way you can drive across in a few days. The distance from Earth to the Moon, 238,000 miles, is large in a way that took Apollo astronauts 3 days to cross. These distances feel large because they are large relative to our bodies, our vehicles, our lifetimes. The distance to Proxima Centauri is 25 trillion miles. Written in full, that number contains 14 digits. If you attempted to count 25 trillion at a rate of 1 number per second without sleeping, without stopping, you would require over 79,000,000 years. Our entire species, Homo sapiens, has existed for approximately 300,000 years. You would need to run our entire evolutionary history more than twice just to finish counting. And Proxima Centauri is the closest star, the nearest one. Our immediate neighbor in a galaxy containing somewhere between 200 and 400 billion stars. The Milky Way itself stretches approximately 1,000,000 light-years from one edge to the other. At 186,000 miles per second at the maximum speed the universe permits, crossing our own galaxy from end to end requires 100,000 years of continuous travel. The observable universe, the sphere of cosmic space from which light has had enough time to reach us since the Big Bang, extends approximately 46.5 billion light-years in every direction. Its total diameter spans 93 billion light-years. These are the distances a human being would need to cross to explore the cosmos, and the fastest machine we have ever built would need 6,600 years to reach the very first star. The Voyager 1 spacecraft provides perhaps the most honest measure of where we actually stand. Launched in September of 1977, Voyager 1 has been traveling continuously for over 47 years. It has never stopped. Its trajectory has taken it past Jupiter, past Saturn, through the outer solar system, and into what scientists call interstellar space, the region beyond the Sun's magnetic bubble where the interstellar medium begins. In 2012, Voyager officially crossed the heliopause, the boundary where the Sun's solar wind loses its battle against the pressure of gas and particles drifting between the stars. Headlines around the world announced that humanity had reached interstellar space, and in one narrow technical sense that was true. In every other sense it was profoundly misleading. Voyager 1 has traveled approximately 15 billion miles from Earth. This is a real distance. It is farther than any human-made object has ever traveled. And yet 15 billion miles measured against the distance to the nearest star represents less than 1/20th of 1% of the journey. If you scale the distance to Proxima Centauri down to the length of a football field, 100 yards from one end zone to the other, Voyager 1's 7-year journey would have covered approximately 2 inches. You would still be standing in the end zone. You would not yet have reached the first yard line. The probe carries a plutonium power source that loses roughly 4 watts of power each year as the radioactive material decays. By the mid-2030s, Voyager will no longer have sufficient power to operate any scientific instruments. Shortly after, it will fall permanently silent, continuing its journey as a dead artifact tumbling through the void. It will drift through interstellar space for tens of thousands of years. It will never reach another star. It will never be seen again by any human eye or any instrument we could ever build. The cold mathematics of chemical propulsion explain why. Every rocket humanity has ever launched, from the first German 5-2 missiles of the Second World War to the Saturn V that carried Apollo astronauts to the Moon, to the Falcon Heavy, lifting commercial satellites into orbit today, operates on the same fundamental principle. Hot gas is expelled from one end of the vehicle. The reaction force pushes the vehicle in the opposite direction. Newton's third law, expressed in fire and exhaust. The efficiency of a rocket is measured by a quantity called specific impulse, essentially how much thrust you extract from each unit of propellant. Chemical rockets, burning the most energetic fuels available, liquid hydrogen combined with liquid oxygen, achieve specific impulse values around 450 seconds. This number represents the ceiling imposed not by engineering but by chemistry itself. When hydrogen and oxygen combine to form water vapor, the energy released by the formation of chemical bonds produces exhaust molecules moving at approximately 4.4 kilometers per second. No combustion reaction can exceed this velocity. The chemistry simply does not permit it. The consequences are encoded in what engineers call the Tsiolkovsky rocket equation, derived by Russian mathematician Konstantin Tsiolkovsky in 1903. This deceptively simple formula relates the velocity a rocket can achieve to two quantities: the exhaust velocity of its propellant and the ratio between the rocket's starting mass and its final mass after burning all its fuel. The equation contains an exponential function, and that exponential is where dreams go to die. To understand what this means in practice, consider what would be required to accelerate a modest spacecraft, something the size of a large car, massing perhaps 1,000 kilograms to just 1% of the speed of light, using chemical propulsion. 1%, not 10%, not 50%, 1% of light speed, which would still require over 400 years to reach Proxima Centauri. The fuel mass required to achieve this velocity exceeds the total mass of the observable universe. Not the mass of Earth, not the mass of the Sun, not the mass of the Milky Way. The mass of every galaxy, every star, every planet, every atom in the entire observable cosmos. All of it combined would not provide enough chemical fuel to push a car to 1% of light speed. This is not dramatic exaggeration. This is what the Tsiolkovsky equation actually demands. The exponential nature of the rocket equation creates a vicious cycle with no chemical escape. To go faster, you need more fuel. But more fuel means more mass. More mass means more fuel required to accelerate that mass, which means yet more fuel. The cycle spirals upward without bound. Every increment of additional velocity demands not just more propellant, but exponentially more propellant, until the quantities required transcend any physical meaning. Gravity assists offer a partial workaround. By carefully timing a flyby of a massive planet, a spacecraft can steal a small fraction of that planet's orbital energy, using the gravitational interaction to accelerate without burning any fuel. The Voyager probes exploited this technique, masterfully receiving boosts from Jupiter and Saturn that sent them toward the outer solar system and eventually into interstellar space. The Parker Solar Probe uses repeated flybys of Venus to gradually build its record-breaking velocities near the Sun. But gravity assists have hard limits. The solar system contains only so many massive bodies positioned only so usefully. A spacecraft optimized across an entire decade of planetary encounters bouncing from planet to planet in a precisely choreographed gravitational ballet might eventually reach velocities approaching 150,000 miles per hour. Still inadequate by a factor of thousands for any meaningful approach to interstellar travel. Ion propulsion improves efficiency dramatically over chemical rockets by accelerating charged particles through electric fields rather than through combustion. The exhaust velocity of an ion engine can reach 40 or 50 kilometers per second, 10 times what chemical rockets achieve. The Dawn spacecraft used ion propulsion to orbit 2 separate asteroids in the main belt, accomplishing maneuvers that would have been chemically impossible. But ion engines generate thrust so small that a single sheet of paper resting on your open palm exerts comparable force. Continuous thrust over years builds velocity, but the velocities achievable within any reasonable mission duration remain far below the threshold where interstellar travel becomes conceivable. The fundamental problem is this: chemical propulsion, ion propulsion, gravity, assists solar sails, all of these technologies operate within the same basic constraint. They can move objects through space. They cannot move objects through space fast enough by margins so vast that incremental improvement offers no path forward. To reach the stars within a human lifetime, something deeper must change. Not better engineering of the same principles, but an entirely different relationship between the traveler and the space they are crossing. That different relationship exists. It was hiding in plain sight within the equations of physics for decades before anyone understood its implications. And it begins not with an engine but with a clock. In the summer of 1958, a group of physicists gathered at a facility in San Diego, California, and asked a question that should have sounded insane. What if the most powerful explosive force humanity had ever unleashed, the nuclear bomb, could be harnessed not for destruction, but for propulsion? What if instead of containing that energy within a reactor, instead of carefully managing and moderating it through layers of shielding and cooling systems, you simply detonated bombs behind your spacecraft one after another and rode the pressure wave outward into the cosmos? The project that emerged from that question was called Orion, and the men who worked on it were not dreamers in the pejorative sense of that word. They were not science fiction enthusiasts spinning fantasies at a kitchen table. Freeman Dyson was one of the most brilliant theoretical physicists of the 20th century, a man whose mind moved comfortably between quantum field theory and the deepest questions of cosmology. Theodore Taylor was a nuclear weapons designer who understood the physics of atomic detonations more intimately than almost any other person alive. Dozens of engineers, mathematicians, and physicists devoted years of serious effort to transforming what seemed like an absurd premise into detailed, rigorous engineering. They built models, small ones using conventional chemical explosives rather than nuclear devices. They detonated charges beneath lightweight pusher plates and watched the models fly. The plates survived the blasts. The shock absorption systems functioned as designed. The concept worked, not in theory, in practice, in actual physical tests conducted in an actual facility by actual engineers measuring actual results. The principle behind Orion is straightforward in its brutality. A spacecraft carries a large supply of specially designed nuclear explosive devices. These devices are ejected one at a time from the rear of the vehicle and detonated at a calculated distance far enough that the blast does not destroy the spacecraft, close enough that the expanding plasma delivers maximum momentum to the pusher plate mounted at the vessel's stern. Shock absorbers between the pusher plate and the crew compartment smooth the violent impulses into something approximating tolerable acceleration. Repeat this process thousands of times over hours and days, and the spacecraft builds velocity in a way that chemical rockets cannot approach. Calculations showed that a modest Orion spacecraft using fission bombs, the relatively simple atomic devices similar to those used at Hiroshima and Nagasaki, could reach velocities between 3 and 4% of the speed of light. Larger designs incorporating hydrogen fusion bombs, thermonuclear devices, far more energetic than fission weapons, might achieve 8 to 10%. The most ambitious designs requiring engineering capabilities beyond what the 1960s could deliver pointed toward 15% of light speed or higher. These numbers represent a genuine revolution compared to anything we have achieved. 15% of light speed versus Voyager's 0.006%. That is an improvement of 2500 times. And yet here, the weight of cosmic distance asserts itself again. Even at 15% of light speed, the journey to Proxima Centauri would require approximately 28 years from the traveler. A human departing Earth in their 30s might survive to see arrival, barely. The nuclear test ban, treaties of 1963, ended Project Orion before any nuclear detonations could be tested. The political moment that made the project possible, the strange window of early Cold War ambition, when governments were willing to fund nearly anything that bore the stamp of nuclear technology, closed before the engineering could mature. The project was cancelled, the detailed plans were archived, and humanity chose, perhaps wisely in the context of terrestrial concerns, not to pursue the path that pointed most directly toward the stars. But Orion's legacy is important, not as a historical curiosity, but as a demonstration of principle. Nuclear pulse propulsion requires no new physics. It demands no exotic materials whose properties remain speculative. It operates entirely within the understood framework of nuclear physics and Newtonian mechanics. The fact that it could achieve 15% of light speed using concepts available in the 1960s reveals something crucial. The barrier between our current velocities and interstellar scale speeds is not a wall built from unknown physics. It is a wall built from choices, political, financial, cultural choices, about what kind of technology to develop. The British Interplanetary Society revisited this territory in 1973, launching a study that would run for 5 years and produce the most detailed engineering blueprint for an interstellar spacecraft ever completed. Project Daedalus, as it was called, examined a 2-stage fusion-powered spacecraft designed to reach Barnard's star approximately 6 light-years from Earth in roughly 50 years cruising at 12% of light speed. The Daedalus design was enormous by any measure. The spacecraft would mass approximately 54000 tons at launch, with the overwhelming majority of that mass being fuel. Pellets of deuterium and helium, 3 each smaller than a marble, would be injected into a reaction chamber at a rate of 250 per second. Powerful electron beams would compress each pellet until the nuclei within it were forced close enough together to fuse, releasing energy that the magnetic nozzle would direct into thrust. The first stage would burn for 2 years, accelerating the spacecraft to 7.1% of light speed before separating and falling away. The second stage would fire for another 1.8 years, pushing the vessel to its final cruise velocity. After that, Daedalus would coast. For 46 years, it would drift through interstellar space at 12% of light speed, carrying no crew. The study concluded that crewing such a mission was impractical for this first design, but carrying an array of scientific instruments and smaller subprobes that would be released during the brief passage through the Barnard's star system. The entire period of useful observation near the target star would last only a few days. Then Daedalus would continue outward forever, its mission complete, its instruments falling silent one by one as power resources depleted. The helium-3 fuel requirement revealed an immediate and sobering obstacle. Helium-3 is extraordinarily rare on Earth. The lunar surface, bombarded for billions of years by the solar wind, contains it in concentrations that make extraction theoretically viable. But the quantities required for Daedalus, approximately 3,000 tons, would demand mining operations on the Moon of a scale that makes the entire history of terrestrial resource extraction look modest. This is not impossible, but it is not close to possible with anything resembling current capability. Project Icarus, begun in 2009 by the British Interplanetary Society and the Tau Zero Foundation, updated the Daedalus work with modern physics and engineering assumptions. The Icarus studies explored different fusion fuel combinations, deuterium-deuterium reactions that avoid the helium-3 supply problem at the cost of lower efficiency, and various engine configurations. The general conclusion confirmed what Daedalus had suggested. Velocities between 10 and 20% of light speed appear achievable with fusion propulsion, using technology that might be developed within the coming century, assuming sustained investment and political will. At 20% of light speed, the journey to Epsilon Eridani, a young sun-like star, approximately 10.5 light-years distant, known to host at least one planetary companion, would require approximately 52 years. From Earth's perspective, a crew departing in their late 20s might, if medicine and biology cooperate, survive to see arrival in their 80s. The margin is razor-thin. The journey consumes virtually an entire human life. And this assumes 20% of light speed, a velocity that represents a 40-fold improvement over anything we have tested using fusion technology that has not yet been demonstrated at the scale required. The gap between 20% of light speed, where human survival on an interstellar journey becomes theoretically conceivable, and 90% of light speed, where time dilation begins to dramatically compress journey duration, represents perhaps the most formidable engineering challenge in the present history of physics. It is a gap that conventional thinking about propulsion cannot bridge. larger fusion reactors, more efficient ion drives, more ambitious gravity assist trajectories. None of these approaches, even in their most optimistic projections, can close that gap. Antimatter propulsion theoretically could. When a particle of matter contacts its antimatter counterpart, a proton meeting an antiproton, an electron meeting a positron, both particles annihilate, completely converting 100% of their combined mass into energy. This is not 80% conversion, not 99%, 100, complete, total. The most energetic chemical reactions convert a fraction of a percent of mass into energy. Nuclear fission converts approximately 0.1%. Nuclear fusion reaches roughly 0.7%. Antimatter annihilation converts 100%, making it the most energy-dense fuel source permitted by known physics. A single gram of antimatter annihilating with a single gram of ordinary matter releases approximately 180 trillion joules of energy. To put this in terms, you can hold in your mind that single gram of antimatter stores the energy equivalent of the atomic bomb dropped on Hiroshima. 1 gram, less than the weight of a paperclip, containing the destructive power that leveled a city. An antimatter rocket would direct the products of matter-antimatter annihilation through a magnetic nozzle. When protons meet antiprotons, the annihilation produces particles called pions moving at a significant fraction of light speed. These pions can be deflected magnetically to generate thrust. The exhaust velocity approaches the speed of light itself, far exceeding what any other propulsion concept achieves. With this exhaust velocity, the Tsiolkovsky equation's cruel exponential becomes manageable rather than catastrophic. Relativistic velocities become mathematically accessible with fuel ratios that do not require impossible quantities of matter. The obstacle is production. Antimatter does not exist naturally in any accessible location in the known universe. Every antiproton used for propulsion must be manufactured by accelerating ordinary protons to extreme energies and smashing them together, occasionally producing antimatter particles in the collision debris. The process is staggeringly inefficient. For every unit of energy stored in the resulting antimatter, approximately 10 billion units of energy must be consumed in the production process. Current global antimatter production at facilities including CERN in Switzerland and Fermilab in the United States totals perhaps 10 to 20 nanograms per year. A nanogram is 1/1,000,000th of a gram. To accumulate 100 kilograms of antimatter, a quantity that might plausibly propel a small probe to 30% of light speed at current production rates, would require 5 billion years. The Sun will exhaust its hydrogen fuel and expand into a red giant in approximately 5 billion years. We would finish collecting our antimatter fuel at approximately the moment Earth becomes uninhabitable. The storage problem compounds the production problem catastrophically. Antimatter annihilates the instant it contacts ordinary matter. Containing it requires magnetic traps that suspend the fuel in perfect vacuum, with the antimatter never touching any physical surface. The longest any antimatter has been successfully contained is measured in hours, a few hours achieved at CERN under laboratory conditions using equipment that fills large rooms and requires continuous power. Scaling from hours of storage to decades of storage during an interstellar journey represents an improvement factor so large it strains comprehension. Beamed energy propulsion sidesteps the fuel mass problem entirely by leaving the energy source at home. A powerful laser array on Earth, or in Earth orbit, directs its beam at a lightweight reflective sail attached to the spacecraft. Photons carry momentum. When they strike the sail and reflect, they transfer that momentum to the vehicle. No fuel need be carried aboard the spacecraft. No reaction mass must be accelerated alongside the payload. The energy source remains stationary, powering the mission from a distance that grows with every passing second. Breakthrough Starshot, announced in 2016 with initial funding of $100 million from investor Yuri Milner, and endorsed by the late Stephen Hawking, represents the most serious modern development of this concept. The project envisions a phased laser array with combined output approaching 100 gigawatts, the equivalent of roughly 100 large nuclear power plants, firing simultaneously into a precisely coordinated beam, accelerating a spacecraft massing only a few grams to 20% of light speed, in approximately 10 minutes. The spacecraft itself would be gossamer, a reflective sail perhaps 4 meters across, connected to a chip-sized payload carrying cameras, communication equipment, and navigation systems. The entire vehicle would weigh less than a standard paperclip. This extreme lightness is not a limitation but a necessity. The laser array can only accelerate what its photon pressure can push to meaningful velocities. A heavier spacecraft requires proportionally more laser power, and the engineering of coherent laser arrays grows catastrophically more difficult as output scales up. At 20% of light speed, a Starshot probe would reach the Alpha Centauri system, our nearest stellar neighborhood, containing 3 stars including Proxima Centauri, in approximately 20 years. It would flash through the system at that velocity, having perhaps minutes of useful observation time before continuing outward forever. The images and data it captured could be transmitted back to Earth, taking 4 years to arrive. Humanity could, within this century, have its first close-up photographs of another star system. But this is a probe, a paperclip-weight sliver of silicon and metal, not a human being, not a vessel capable of sustaining life across interstellar distances. And the fatal limitation of laser sail propulsion becomes immediately apparent when you consider what a human crew would require. Deceleration. A laser sail accelerates by reflecting light from behind. At the destination, no laser exists to push back against the incoming spacecraft. Nothing can slow the vessel. A human crew arriving at Alpha Centauri at 20% of light speed would flash through the system in minutes, unable to stop, unable to explore, unable to do anything but observe through rapidly receding windows before vanishing into the interstellar void beyond. The journey would be one way in the most literal and useless sense. Not a voyage of exploration, a flyby, a missed connection at cosmic scale. This is where the engineering wall becomes visible in its full height and its full despair. Every propulsion concept that achieves meaningful interstellar velocities fails in a different way. Nuclear pulse propulsion works in principle but was abandoned for political reasons and faces fresh obstacles in a world where nuclear technology is among the most tightly regulated in existence. Fusion propulsion offers 15 to 20% of light speed, enough to reach the nearest stars within a human lifetime barely, while consuming that lifetime entirely in transit. Antimatter offers the physics of a solution with production and storage requirements that may never be practically achievable. Beamed laser propulsion can accelerate gossamer probes to impressive velocities, but cannot decelerate human crews at their destinations. And all of these concepts share the same fundamental failing. They cannot reach the velocities above 70, 80, 90% of light speed, where time dilation transforms interstellar travel from survival into something genuinely livable, where a journey to another star system compresses from a lifetime's ordeal into a passage of years or decades, where the physics of time itself becomes the traveler's greatest ally. To cross that threshold requires not better versions of propulsion systems we already understand, but a fundamentally different relationship between the spacecraft, its energy source, and the structure of spacetime. It requires perhaps exploiting the same physics that makes speed so costly in the first place. The same equations that demand exponentially more energy for each additional increment of velocity also contain encoded within them the promise that sufficiently high velocities carry a reward no amount of additional engineering can replicate. The reward is time, or rather the absence of it. And to understand that reward, we must return to Bern, Switzerland, to a small apartment near the patent office, to a young man sitting in the failing light of a late afternoon in 1905 with a pencil and a notebook and a question that would take him to the edge of what a human mind could contain. He asked, "What is time really?" Not what we assume it to be. Not the universal constant that flows at the same rate for every observer, ticking steadily through every corner of the cosmos in perfect metronomic uniformity, but what it actually is when you strip away every assumption and look at what the physics demands. The answer he found would shatter 3 centuries of certainty, and it would open a door in the wall that every rocket, every ion drive, every nuclear detonation had failed to breach. The apartment at 49 Kramgasse in Bern, Switzerland, is an ordinary building on an ordinary street in an ordinary European city. The rooms are modest, the ceilings are not particularly high, the windows look out onto a cobblestoned lane where the sounds of the city drift upward in the afternoons, the clatter of horses, the voices of shopkeepers, the distant mechanical chiming of the famous clock tower at the end of the street. In 1905, a young man lived in those rooms with his wife and their infant son. He worked 6 days a week at the Federal Patent Office, examining technical drawings and written descriptions of new inventions, evaluating whether the underlying concepts were sound, whether the claims were valid, whether the mechanisms described would actually function as their inventors hoped. It was not glamorous work. It was not the academic position he had sought and failed to obtain after graduating from university. It was a job, a way to pay rent and buy food while he continued in the hours before and after the office to think. Albert Einstein was 26 years old in 1905. He held no professorship, no laboratory, no research funding. He had no graduate students to help develop his ideas, no colleagues in proximity to challenge his reasoning, no institutional prestige to lend authority to his conclusions. He had a patent office desk a few hours each day before the demands of work and fatherhood absorbed his attention, and a mind that could not stop asking questions that everyone else had decided were already answered. The question that consumed him most deeply in that period concerned light. Specifically, it concerned what you would see if you could somehow travel alongside a beam of light, if you could match its velocity and ride next to it through space, the way you might ride alongside a river current and watch the water move beside you. In classical physics, the answer seemed obvious. If you matched the speed of the river, the water next to you would appear still. If you matched the speed of light, the electromagnetic wave traveling beside you should appear frozen, a static ripple in the fabric of space, motionless relative to your position. But Maxwell's equations, which govern the behavior of light and electromagnetism, do not permit this. They describe light as a wave that propagates at a fixed speed determined by fundamental constants of nature. These equations contain no provision for the wave appearing stationary to any observer. They insist with mathematical stubbornness that light always moves at the same speed, always 186.282 miles per second, regardless of the motion of the observer measuring it. Einstein took this insistence seriously in a way that no one before him had fully committed to. He decided that if the equations said light speed was constant for all observers, then the equations were right. Not approximately right. Not right under certain conditions. Exactly and universally right, without exception for every observer in every state of motion anywhere in the cosmos. From this single commitment, everything else followed with the cold inevitability of mathematics. If light speed must remain constant for all observers regardless of their motion, then something else must give way. Something that had always been assumed to be fixed, universal, and identical for every observer in every location. That something was time. Consider two observers. One stands motionless on a platform, the other passes by on a train moving at a significant fraction of light speed. Both observers carry identical clocks. Both clocks were synchronized to the same time before the train began moving. As the train passes the platform, both observers measure the speed of a beam of light traveling parallel to the track. Both must measure the same value, 186.282 miles per second. This is the constraint Einstein accepted absolutely. But the observer on the platform sees the train moving. The observer on the train sees the platform moving. Their relative states of motion are genuinely different, and yet both must measure the same light speed. How can this be mathematically consistent? The only resolution, the only way the equations can balance, is if time itself runs at different rates for the two observers. The clock aboard the train must tick more slowly than the clock on the platform, not because of any mechanical defect in the train's clock, not because of vibration or temperature or any physical effect acting on the clock's mechanism, but because time itself, the actual rate at which moments succeed one another, the actual pace at which the universe ages, runs more slowly for the observer in motion. This effect is called time dilation, and it is not a theoretical curiosity that exists only in the rarefied world of thought experiments. It is a measurable, verified, experimentally confirmed feature of physical reality that has been tested thousands of times using clocks accurate enough to detect the minuscule time differences produced by everyday velocities. In 1971, physicists Joseph Hafele and Richard Keating placed cesium atomic clocks aboard commercial airliners and flew them around the world east and then west, comparing their readings afterward to identical clocks that had remained stationary at the United States Naval Observatory in Washington. Airplanes travel at roughly 600 miles per hour. This is not remotely close to the speed of light. The time dilation effect at such velocities is almost unimaginably small, and yet the flying clocks had gained or lost nanoseconds, billionths of seconds, in precise agreement with what relativity predicted. The effect was real, measurable, exactly as Einstein's equations demanded. The GPS satellite network that guides the navigation systems in your phone depends on corrections for time dilation to function accurately. The satellites orbit Earth at approximately 14,000 kilometers per hour. At this velocity, their onboard clocks run slightly slower than clocks on the ground by about 7 microseconds per day due to velocity-based time dilation. Without correcting for this effect, GPS position calculations would accumulate errors of several kilometers per day, rendering the system useless within hours of operation. Every time your phone navigates you to a destination, it is benefiting from Einstein's 1905 insight about the nature of time. The magnitude of time dilation depends on velocity, and the relationship between them is captured in a quantity that physicists call gamma, the Lorentz factor, named after Dutch physicist Hendrik Lorentz, who derived related mathematics before Einstein provided their physical interpretation. Gamma tells you exactly how much time slows for a moving observer relative to a stationary one. At low velocities, gamma barely differs from 1, meaning time runs at essentially the same rate for moving and stationary observers. This is why time dilation is not part of everyday human experience. At the velocities we inhabit, walking, driving, flying, the effect is too small to notice without extraordinarily precise instruments. But as velocity climbs toward a significant fraction of light speed, gamma begins to rise, and the way it rises is not gradual or linear. It accelerates. It climbs slowly at first, then faster, then with increasing urgency, then with a kind of mathematical violence as velocity approaches its absolute ceiling. At 50% of light speed, gamma reaches approximately 1.15. For every year that passes aboard a spacecraft moving at half light speed, roughly 14 months pass on Earth. The difference is noticeable, but not transformative. A traveler departing on a 50-year journey at this velocity would return having aged 50 years, while Earth aged 57. Their children would be slightly older than expected. Their grandchildren might find this interesting. At 90% of light speed, gamma jumps to approximately 2.3. Now the compression becomes meaningful. For every year experienced by the traveler, 2 years and 4 months pass on Earth. A journey lasting 20 subjective years spans 46 years of Earth time. A crew member departing at age 30 would return at 50, finding their peers approaching 80. At 99% of light speed, gamma reaches 7.1. The transformation accelerates dramatically. 7 years pass on Earth for every year experienced aboard the spacecraft. A decade of ship time spans 70 years of human history. A 20-year journey, a career, a major chapter of a human life, encompasses 140 years on Earth. The traveler would depart from one world and return to something unrecognizable, separated from their point of departure by more time than separates us from the American Civil War. At 99.9% of light speed, gamma exceeds 22. 22 years of Earth time compress into a single year of ship time. A journey spanning 50 subjective years, a long working life, a full arc of adult experience covers more than 1,000 years of Earth history. The civilization that launched the traveler would be as remote from the returnee as the medieval period is from us. Languages transformed beyond recognition, political systems risen and fallen, technologies unimaginable at departure now mundane. Each additional 9 added to the velocity 99.99%, 99.9999%, 99.9999% multiplies gamma by roughly a factor of 3. At 99.99% gamma exceeds 70. At 99.9999%, it surpasses 223. At 99.9999%, it climbs past 707. The numbers grow with a kind of terrible beauty, each increment of velocity purchasing an ever greater compression of time for the traveler, while Earth ages at its normal pace outside the spacecraft's reference frame. To feel what this means at a human scale, consider a specific journey. Vega is one of the brightest stars visible from Earth's northern hemisphere. It anchors the Summer Triangle asterism, burning blue-white in the constellation Lyra at a distance of approximately 25 light-years. From Earth's perspective, a spacecraft traveling at 99% of light speed would require approximately 25 years and 2 months to cross this distance. Light speed is light speed, and the journey's duration measured by external clocks cannot compress below the time light itself requires to traverse the same path. But aboard the spacecraft, gamma at 99% equals 7.1. The traveler's own experience of time, their heartbeats, their metabolic processes, the aging of their cells, the passage of their thoughts runs at 1/7 the rate of Earth time. The 25-year journey measured from Earth compresses to roughly 3.5 years of subjective experience for the traveler. They eat perhaps 1,200 meals during the crossing. They sleep perhaps 1,300 nights. They age, biologically and experientially, by 3.5 years. They arrive at a star 25 light-years from home, having consumed less time than a typical university degree. Push velocity to 99.9% and gamma exceeds 22. That same journey to Vega, still 25 light-years in objective distance, compresses to barely over a year of subjective time. The traveler crosses 25 light-years, a distance that would require 6600 years at humanity's current maximum velocity in approximately 13 months of personal experience. They could make the round trip to Vega and back, traveling both legs at 99.9% of light speed, and return to Earth, having aged roughly 2.5 years, while Earth aged 50. They would return to find that everyone they had known at departure was elderly or gone. Their children, if they had any, would be in their 50s. Their parents would almost certainly be dead. The world would have moved through half a century of history during their 2.5-year absence. This is the twin paradox made concrete and personal, not an abstract thought experiment, but a lived reality with human consequences that no amount of intellectual preparation can fully soften. The twin paradox troubled early critics of relativity precisely because it seemed to contain a logical contradiction. Motion is relative. If Alice boards a spacecraft and moves away from Bob at 99% of light speed, then from Alice's perspective, it is Bob who is moving away at 99% of light speed. Why should Alice age less rather than Bob? If motion is truly relative, shouldn't the aging difference be symmetric? The resolution lies in a physical asymmetry that motion alone cannot eliminate. Alice accelerated. She experienced the force of her spacecraft's engines pushing her out of Earth's gravitational field-building velocity, eventually reaching cruise speed. Bob experienced nothing. He remained in his reference frame without any net force acting on him across the duration of Alice's journey. When Alice decelerates at her destination and eventually turns around to return, she again experiences acceleration, the forces necessary to change her velocity and point her back toward Earth. Bob again experiences nothing. Acceleration is not relative. You can always tell from the inside whether you are accelerating or not. A scale placed on the floor of Alice's spacecraft during the acceleration phase would read her weight. The engine's thrust pushes the floor up against her feet, exactly as gravity pushes Earth's ground up against Bob's feet at home. The asymmetry of their experiences breaks the apparent symmetry of their relative motion and determines unambiguously that Alice will be younger than Bob when they reunite. This asymmetry has been confirmed experimentally, not just with Hafele and Keating's airplane clocks, but with particle accelerators that routinely produce unstable subatomic particles moving at significant fractions of light speed. Muons, particles similar to electrons but 207 times heavier, are produced in Earth's upper atmosphere when cosmic rays strike air molecules. They are unstable, decaying with a half-life of approximately 2.2 microseconds when at rest. At the velocities they achieve in the upper atmosphere, typically above 98% of light speed, their half-life, measured by ground-based instruments, extends by a factor of roughly 10 or more. They survive long enough to reach detectors at Earth's surface, crossing distances that their rest frame half-life would render impossible. The muons do not know they are supposed to decay quickly. They are not cheating. They are simply experiencing time at the rate appropriate to their velocity, dramatically slower than the rate at which ground-based observers experience it. Their extended survival is not an illusion. It is exactly what Einstein's equations predict, and it has been measured, confirmed, and relied upon by physicists for decades. The visual experience of travel at these velocities would be unlike anything human perception has encountered. As a spacecraft accelerates toward light speed, the light arriving from stars ahead becomes compressed in wavelength, blue-shifted, in the language of wave physics, with the degree of compression increasing as velocity rises. Stars that appear yellow at low speeds shift toward blue, then toward violet, then into ultraviolet frequencies invisible to the naked eye. At extreme velocities, the forward-facing stars emit primarily X-rays and gamma rays detectable only by instruments rather than human senses. Simultaneously, a phenomenon called relativistic aberration distorts the apparent positions of all stars across the sky. Light arriving from the sides of the spacecraft appears to come from slightly ahead of the beam, as though the universe itself were leaning toward the direction of travel. As velocity climbs, this aberration becomes more pronounced. At 90% of light speed, the visible universe appears compressed into a forward-facing cone spanning roughly 60 degrees. At 99%, this cone shrinks to 16 degrees. The entire cosmos, the totality of all visible stars and galaxies, crowds into a narrowing circle directly ahead, surrounded by an expanding ring of darkness, where the sky behind has gone completely black, its light redshifted beyond any detectable frequency. A traveler at extreme relativistic velocities would see the universe not as a sphere of stars surrounding them on all sides, but as a single blazing disk of light dead ahead. Its colors shifted wildly from the familiar palette of normal starlight, with absolute darkness pressing in from every other direction. It would be beautiful in the way that some things are beautiful precisely because they are inhuman, existing at a scale and in a mode that no biological creature was designed to experience. The interstellar medium presents physical hazards that scale with velocity in ways that become increasingly dangerous at high fractions of light speed. The space between stars is not perfectly empty. Each cubic centimeter contains, on average, approximately one hydrogen atom, along with traces of heavier elements and microscopic dust particles. At the velocities of current spacecraft, these particles are essentially irrelevant. Voyager 1 has been passing through them for decades without consequence. At 90% of light speed, each hydrogen atom encountered by the spacecraft carries kinetic energy comparable to a high-energy cosmic ray. The spacecraft's forward surfaces are bombarded continuously by particles that, from the traveler's reference frame, arrive as a dense radiation field capable of damaging electronic components, degrading materials at the molecular level, and penetrating biological tissue. At 99%, the energy of each particle impact increases by another factor of 7. At higher velocities still, the forward radiation environment becomes severe enough to require substantial shielding, adding mass that must itself be accelerated to relativistic velocities, compounding the already daunting energy requirements. These are genuine engineering obstacles. They are not necessarily insurmountable, but they demand solutions that do not yet exist. Magnetic shielding, generating powerful fields ahead of the spacecraft to deflect charged particles before they reach the hull, appears theoretically workable. Physical shielding using dense materials can absorb radiation but adds mass. Some combination of the two approaches perhaps augmented by active sensing and evasion systems that detect dense regions of interstellar material ahead and adjust trajectory accordingly, might suffice for velocities below 99% of light speed. But none of these technical complications alter the fundamental promise encoded in the mathematics of time dilation. The universe genuinely compresses time for fast-moving travelers. This is not an approximation. It is not a convenient fiction that breaks down when examined carefully. It is a precisely quantified feature of physical reality, confirmed by experiments ranging from atomic clocks on airliners to subatomic particles in accelerators to the satellite navigation systems guiding cars and ships and aircraft around the planet every moment of every day. The question is no longer whether time dilation is real. The only remaining question is whether humanity can ever build spacecraft capable of exploiting it. And that question brings us back to engines, not the chemical rockets that brought us this far, not the ion drives and gravity assists that represent the current frontier, but something fundamentally different. Something that could bridge the gap between 20% of light speed, where we might barely survive a journey to the nearest stars, and 90 or 99%, where the universe opens like a door and every star in the galaxy becomes theoretically reachable within a human lifetime. The physics permits it. The equations do not forbid it. What they demand instead is energy on a scale that staggers the imagination and propulsion concepts that push the boundaries of what engineering has ever attempted. The energy problem is the first thing you must understand. Before any discussion of engines, of fuels, of clever engineering solutions, the raw mathematics of what relativistic travel demands must be confronted directly without softening, without the comfort of vague optimism about future technological progress. To accelerate 1 kilogram, a single kilogram less than the weight of a standard water bottle, to 90% of light speed, requires approximately 43 quadrillion joules of energy. Written out, that number contains 16 digits. It equals the total electricity consumed by the entire United States across approximately 4 years of continuous operation for 1 kilogram. A spacecraft capable of carrying a human crew across interstellar distances might mass hundreds of thousands of kilograms. The energy required scales proportionally. At 99% of light speed, the requirement multiplies by a factor of roughly 7, the same gamma factor that governs time dilation, now working against the engineer rather than for the traveler. At 99.9%, the factor exceeds 22. Each increment of velocity toward the absolute ceiling demands exponentially more energy for diminishing returns in speed, even as the time dilation benefit grows with each additional fraction of a percent. This is the energy wall. It is real, it is quantified, and it explains why every propulsion concept humanity has seriously studied, from chemical rockets to nuclear pulse systems to fusion drives, falls short of the velocities where time dilation transforms interstellar travel into something a single human life can encompass. But the wall has cracks, and some of those cracks have been studied by serious scientists working within the constraints of understood physics, not speculating about exotic new forces or undiscovered principles, but asking what the laws we already know will permit if we are willing to invest the engineering effort those laws demand. The most serious near-term crack is nuclear pulse propulsion, and its story deserves to be told not as a historical footnote, but as an active warning about what humanity has already surrendered. When Project Orion was cancelled in 1963, the engineers working on it did not believe they were abandoning a fantasy. They believed they were abandoning a spacecraft. Freeman Dyson estimated in later years that an Orion vessel could have reached Mars within a decade of the program's inception, using technology available in the early 1960s. Not a flyby, not a robotic probe, a crewed vessel landing on Mars, returning to Earth using nuclear detonations for propulsion. The interstellar variant of the Orion concept, sometimes called the Orion battleship in internal documents, for reasons that reveal something about the scale being contemplated, would have massed millions of tons. It would have carried thousands of nuclear devices, detonating one approximately every 3 seconds during the acceleration phase. The pusher plates spanning the ship's stern would have measured hundreds of meters across. The shock absorption system would have been the largest mechanical structure ever built. and the vessel would have been capable, according to the calculations Dyson and his colleagues performed, of reaching 8 to 10% of light speed, enough to deliver a crew to the nearest stars within a century of travel. A century, longer than a human lifetime, but not by much with the right crew selection, and with life extension technologies that might plausibly emerge within the coming generations, not impossibly longer than what motivated humans might endure. The political decision to abandon this path was made for understandable reasons. Nuclear test ban treaties were necessary for planetary survival during the Cold War. A spacecraft launching from Earth's surface while detonating hundreds of nuclear bombs in the atmosphere was not compatible with a world trying to step back from nuclear brinkmanship. The reasoning that ended Orion was sound in its own context, but the cost of that decision measured in the currency of cosmic exploration may never be fully calculated. The most energetically promising propulsion concept grounded in understood physics is the matter-antimatter rocket, and its theoretical performance is almost obscene in comparison to everything else on the table. A rocket expelling the products of proton-antiproton annihilation at velocities approaching light speed itself could in principle achieve gamma factors above 10, with fuel mass ratios that the Tsiolkovsky equation does not render absurd. A spacecraft massing 1,000,000 kilograms at cruise, enough to sustain a small crew across decades of interstellar travel, could theoretically be accelerated to 90% of light speed, with perhaps 6,000,000 kilograms of antimatter fuel, a 6-to-1 fuel ratio, demanding by the standards of chemical rocketry but not the universe-consuming quantities that chemical propulsion would require for comparable velocities. The physics of the annihilation drive works as follows. Protons and antiprotons are brought together in a reaction chamber at a controlled rate. Their annihilation produces pions, subatomic particles that carry the energy of the annihilated mass and move at velocities between 80 and 94% of light speed. Charged pions can be deflected by magnetic fields directed through a magnetic nozzle to produce thrust. Neutral pions decay almost immediately into gamma rays, which carry energy but cannot be magnetically directed and instead require shielding to protect the crew. The efficiency of converting annihilation energy into directed thrust depends on the sophistication of the magnetic nozzle design, but theoretical efficiencies approaching 60 or 70% appear achievable within understood physics. At 60% efficiency and 90% of light speed, the time dilation factor of 2.3 compresses a 25 light-year journey to Vega into roughly 11 years of subjective experience. A crew departing Earth in their late 20s would arrive at Vega in their early 40s. They would still be vigorous, still capable of exploration, observation, the complex physical and intellectual demands of operating in an alien stellar environment. They would have consumed perhaps half their remaining life expectancy in transit, arriving at a destination that no human eye has ever seen from close proximity. This is not survival. This is exploration. Push the antimatter drive to 99% of light speed, and the numbers transform into something that seems to belong to mythology rather than engineering. Vega, in less than 4 years of subjective time. The Pleiades cluster 440 light-years distant in approximately 63 years of ship time, arriving at age 90 if you departed at 27, still achievable within a single extended human lifetime, with the medical advances that the coming century may plausibly deliver. The production problem does not disappear by acknowledging it. It simply sits there immovable like a mountain range between the engineering concept and its implementation. Humanity currently produces perhaps 15 nanograms of antiprotons per year across all operating particle accelerator facilities combined. The 6,000,000 kilograms of antimatter required for the mission described above exceeds current annual production by a factor so large the comparison loses meaning. It would require producing antimatter at roughly 10 billion times the current rate for approximately 10 billion years. Some theorists have proposed that naturally occurring concentrations of antimatter might exist in deep space regions where the slight asymmetry between matter and antimatter in the early universe produced pockets of antimatter-dominated material that have survived to the present. No observational evidence supports this hypothesis. The universe we can observe appears overwhelmingly matter, dominated in every direction telescopes can peer. If antimatter reserves exist somewhere in the cosmos, they remain beyond our detection. Production efficiency improvements offer a more realistic path. Current antimatter production converts roughly 1 part in 10 billion of input energy into stored antimatter energy. Even improving this ratio by a factor of 1,000 to 1 part in 10 million would require centuries of continuous production at civilization-scale energy inputs to accumulate mission-grade quantities. The engineering required to achieve such efficiency improvements does not yet exist even on paper. But it does not obviously violate any physical law. It represents an engineering challenge rather than a physical impossibility, which is a fundamentally different category of obstacle. Beamed propulsion offers an entirely different approach to the energy problem, and its elegance deserves careful attention even though its limitations are equally profound. The central insight is that the most difficult part of interstellar propulsion, providing enormous quantities of energy to a spacecraft traveling at extreme velocities, need not be solved by the spacecraft itself. The energy source can remain stationary, beaming power to the vehicle across the growing distance between them. Breakthrough Starshot's laser sail concept has already been described, but laser propulsion for human-scale spacecraft requires thinking at considerably larger scales than a paperclip weight chip riding a 4-meter sail. A vessel capable of sustaining human life, carrying air, water, food, radiation, shielding medical equipment, scientific instruments, and the structural mass to hold all of this together against the stresses of acceleration might mass several thousand tons even with the most aggressive mass reduction engineering imaginable. To accelerate several thousand tons to 90% of light speed using laser pressure requires a laser array of incomprehensible power output. The photon pressure per unit of laser power is fixed by physics. More mass means proportionally more photons required. More photons means proportionally more laser power. The numbers scale linearly with spacecraft mass, and the result for a human-capable vessel points toward laser arrays with power outputs in the range of 1,000,000 to 10 million gigawatts. The entire current electrical generating capacity of human civilization is approximately 8 gigawatts. The laser array required would need to exceed global power production by factors of 10,000 to a million. This is not a near-term engineering program. It is a goal for a civilization that has solved its energy problems so completely through fusion power, through space-based solar collection, through technologies not yet conceived, that power at these scales is available for allocation, to exploration rather than survival. Such a civilization is not obviously impossible. It is merely distant. The deceleration problem that ruins laser propulsion for robotic probes becomes even more severe for human missions. A crew arriving at a distant star at 90% of light speed without means of deceleration does not conduct an exploration mission. They conduct a brief, terrifying passage through an alien stellar system and continue outward into the void forever. Solutions exist in principle. A magnetic sail using superconducting loops could interact with the stellar wind of the destination star, gradually shedding velocity over months or years of approach. The interstellar medium itself provides some braking through the drag produced by sweeping up interstellar hydrogen, the same effect that makes the Bussard ramjet concept work in reverse. But engineering these deceleration systems to function reliably after decades of interstellar transit, with no possibility of maintenance or repair from Earth, represents a challenge of formidable complexity. Hybrid propulsion architectures attempt to distribute these burdens across different systems optimized for different phases of the mission. A spacecraft might be laser boosted from Earth orbit to 20% of light speed during an initial acceleration phase lasting weeks or months. An onboard fusion drive burning deuterium fuel collected or refined in the outer solar system would extend velocity to 30 or 40% of light speed during a secondary acceleration phase. At the destination, a magnetic sail would begin the long process of deceleration, with the fusion drive providing final braking thrust for orbital insertion. Each component of such a hybrid architecture has been studied individually. The laser array represents the most speculative element, requiring power levels far beyond current capability. The fusion drive pushes against the frontier of what current physics experiments are beginning to demonstrate. The magnetic sail faces engineering challenges in superconductor reliability over decade-long timescales. But no component requires new physics. Each represents an engineering extrapolation from principles already understood. The timeline for such technologies remains genuinely uncertain, not because the engineering is mysterious, but because the pace of development depends on choices that have not yet been made. Investment decisions, policy priorities, international cooperation frameworks, the degree to which humanity's coming decades are consumed by terrestrial problems versus directed toward the long-term expansion of civilization beyond its home planet. Physics does not set the timeline, human choices do. There exists one propulsion concept that sits at the boundary between serious physics and speculation that has attracted sustained attention from credentialed researchers while remaining far from any demonstrated principle. It is worth examining not because it is likely to be implemented soon, but because it illustrates how the constraints that seem absolute can sometimes prove to be less absolute than they appear. In 1960, physicist Robert Bussard proposed what became known as the ramjet. The concept exploited the same interstellar hydrogen that represents a radiation hazard for fast-moving spacecraft, using it instead as fuel. A spacecraft equipped with an enormous magnetic scoop, spanning perhaps thousands of kilometers in effective collection diameter, would sweep up interstellar hydrogen as it traveled, funneling this collected material into a fusion reactor. The reactor would burn the hydrogen, expelling exhaust to generate thrust. The faster the spacecraft traveled, the more hydrogen it collected per unit time, the more thrust it generated. In principle, the ramjet could accelerate indefinitely, limited only by the relativistic mass increase that ultimately prevents any object from reaching light speed. The vision captured imaginations. Spacecraft that carried no fuel at all, sustained entirely by the ambient medium they traveled through, achieving arbitrarily high velocities given sufficient time and distance. Science fiction embraced the concept enthusiastically, and serious physicists devoted attention to refining the engineering details throughout the 1970s. The fatal flaw emerged from those same detailed calculations. The interstellar medium contains approximately 1 hydrogen atom per cubic centimeter on average. Collecting enough hydrogen to sustain fusion at useful rates requires sweeping an enormous volume of space per second. The magnetic scoop necessary to collect this volume creates electromagnetic drag resistance from interacting with the very medium being harvested that exceeds the thrust the fusion drive can generate. The spacecraft would decelerate rather than accelerate. The harder the engine pushed, the harder the scoop dragged back against the motion. More recent calculations have refined this picture somewhat. In unusually dense regions of the interstellar medium, within giant molecular clouds near active star-forming regions, the hydrogen density might be high enough for the thrust to overcome the drag. But these regions are not the typical environment of interstellar space, and navigating to them requires first crossing vast volumes of ordinary low-density medium where the ramjet cannot function. The dream of indefinite acceleration on harvested fuel appears to be precisely that. A dream. Where does this leave us? The honest answer is that humanity currently possesses the theoretical understanding necessary to design interstellar propulsion systems capable of reaching meaningful fractions of light speed. Nuclear pulse propulsion could achieve 8 to 15% of light speed with engineering extensions of demonstrated principles. Fusion drives could reach 15 to 20%. Antimatter annihilation offers a theoretical path to 90% and beyond, constrained not by physics, but by production and storage challenges of daunting magnitude. Laser beaming could accelerate Gossamer probes to 20% and human-scale vessels to significant fractions of light speed if civilization-scale power infrastructure existed to support the beam. None of these technologies in their current state of development can carry a human being to even the nearest star within a comfortable lifetime. The nearest approach fusion propulsion at 15 to 20% of light speed delivers a crew to Proxima Centauri in 20 to 25 years of transit time, while consuming all or nearly all of their remaining functional life in the process. The time dilation benefit at these velocities is minimal. The compression of journey time is measured in months, not years or decades. To cross the threshold where time dilation becomes truly transformative, where a journey spanning 25 light-years compresses to 4 years of subjective experience instead of 25, requires velocities above 90% of light speed, and the gap between 20% where current conceptual engineering points and 90% where the physics becomes generous to the traveler remains the single most formidable barrier in all of exploration science. Yet the universe does not forbid crossing it. The equations that make it so costly to approach light speed are the same equations that make the approach so rewarding. Every fraction of a percent gained above 90% purchases a greater compression of journey time than the same fraction gained at lower velocities. The mathematics is not designed to frustrate travelers. It is designed, in a sense, to reward the most ambitious ones, those willing to pay the highest price in energy for the right to experience time at a radically slower rate than the universe around them. Assume for a moment that the engineering challenges are solved, not by wishful thinking, but by the accumulated progress of centuries of civilization, fusion power, made practical antimatter, production scaled to industrial levels, magnetic containment perfected across decade-long timescales, laser, arrays built in orbit at powers that dwarf current generating capacity. Assume that velocities of 99 or 99.9% of light speed become achievable for human-carrying vessels. Assume that the price in energy has been paid. What then becomes accessible? What distances fall within the reach of a single human life? The answers to these questions do not emerge from engineering. They emerge from the mathematics of time dilation combined with the geometry of the cosmos, from calculating not merely how far a body can travel in 80 years of ship time at extreme velocities, but what those destinations actually are, what exists at those distances, what a traveler arriving after a lifetime of transit would actually find. Having crossed distances that light itself requires centuries or millennia to traverse, the numbers, when you work through them carefully, are not merely impressive, they are devastating in their generosity. Begin with a single human life, 80 years, not 80 years of rest and waiting, but 80 years of active experience of perception, of thought, of biological aging measured in heartbeats and cell divisions and the slow accumulation of memory. 80 years is what most humans in the developed world can reasonably expect with modern medicine, with reasonable fortune, with no catastrophic interruption. It is not a long time by cosmic standards. It is not long by the standards of geology, or evolution, or the lifespan of stars, but it is what we have. It is the temporal budget each human being receives at birth, and the question before us now is what that budget can purchase when spent at the right velocity. The answer depends entirely on how fast you are willing to go. At 90% of light speed, gamma equals approximately 2.3. For every year that passes aboard the spacecraft, 2.3 years pass on Earth. An 80-year journey measured in ship time corresponds to roughly 184 years of Earth time. This velocity is already far beyond anything humanity has achieved, requiring propulsion technologies decades or centuries ahead of current capability. Yet in terms of what it permits, in terms of what destinations it unlocks within a single human lifetime, 90% of light speed is almost conservative. At this velocity, 80 years of ship time carries a traveler approximately 73 light-years from Earth. The surrounding volume of space within 73 light-years contains roughly 2000 star systems. Among them are stars that astronomers have studied in detail from Earth Tau Ceti, 11.9 light-years distant, a sun-like star with confirmed planetary companions, including at least one candidate in the habitable zone. Epsilon Eridani, 10.5 light-years away, younger than our Sun, still surrounded by a debris disk that may be coalescing into a mature planetary system. 61 Cygni, a binary system, 11.4 light-years from Earth, the first star beyond our Sun to have its distance measured accurately achieved by German astronomer Friedrich Bessel in 1838, using the technique of stellar parallax, the apparent shift in a star's position as Earth moves from one side of its orbit to the other. Bessel spent months of careful observation to determine that 61 Cygni lay approximately 10 light-years away. He announced the result to the Berlin Academy in 1838 as one of the great achievements of observational astronomy. The star had been catalogued, named, and studied for decades before anyone knew how far it was. Now we know it hosts two orange dwarf stars orbiting each other, gravitationally bound, with at least one confirmed planetary companion detected through the wobble these planets induce in their parent star's motion across the sky. At 90% of light speed, 61 Cygni lies less than 6 years of ship time from Earth. A traveler departing in their 20s would arrive in their early 30s, having crossed to a stellar system whose distance Bessel labored years to merely measure. They would find two suns in the sky, where we have one each smaller and cooler than our own burning, with a reddish-orange light that gives every surface a warmth unlike any illumination on Earth. Any planets in the habitable zone of this system receive a different quality of radiation than Earth does, cooler, redder, with different implications for any photosynthetic chemistry that might have emerged there. This is what 90% of light speed purchases within the first fraction of an 80-year journey. Not the nearest star, not a single destination, a neighborhood. A volume of space containing 2,000 systems, dozens of which have been studied closely enough that we know something real about what exists there. But 90% is where we begin. The mathematics become genuinely extraordinary when velocity climbs higher. At 99% of light speed, gamma reaches 7.1. 80 years of ship time now corresponds to roughly 568 years of Earth time. More significantly, 80 years of ship time at this velocity carries a traveler approximately 570 light-years from Earth. The sphere of accessible space expands dramatically, not proportionally, but explosively. When 90% of light speed enclosed a volume 73 light-years in radius, 99% encloses a sphere nearly 8 times larger in radius and more than 500 times larger in total volume. Within 570 light-years of Earth lies a cosmos that begins to look genuinely alien compared to our immediate stellar neighborhood, the Hyades cluster, the nearest open star cluster to our solar system. A loose grouping of several hundred stars sharing a common origin lies approximately 153 light-years distant. At 99% of light speed, a traveler reaches the Hyades in roughly 22 years of ship time. They would find themselves surrounded by stars that formed together from the same molecular cloud, perhaps 625 million years ago, stars that began their lives as siblings and have since drifted apart on slightly different trajectories through the galaxy. The Hyades contains stars at various stages of the stellar life cycle, from young blue-white stars burning hot and fast to older orange and red dwarf stars that will outlive the Sun by billions of years. Studying a cluster like the Hyades from within, not from 153 light-years away through Earth's atmosphere and the intervening dust, but from among its constituent stars, would provide astronomical data of a quality no Earth-based or Earth-orbiting telescope could approach. The three-dimensional structure of the cluster, the precise motions of individual stars relative to their neighbors, the distribution of any planetary systems within the cluster's gravitational embrace, all of this would be accessible in a way that remote observation can never replicate. At 570 light-years, an 80-year journey at 99% of light speed reaches something that has captured human imagination since the first clear winter night any human being looked upward and noticed it. The Pleiades, the Seven Sisters, the star cluster that appears in the mythology of cultures, separated by oceans and millennia in Greek mythology as the daughters of Atlas and Pleione, transformed into stars by Zeus to spare them from the hunter Orion's pursuit. In Japanese culture, as Subaru, the word still used for the automaker, whose logo depicts the cluster's 6 brightest stars, in Aboriginal Australian traditions as the Makara, in Hindu astronomy as the Kritika, in the traditions of the Lakota people of North America. Virtually every culture that has ever looked at the winter sky has noticed the Pleiades, named them woven stories around them. They lie approximately 440 light-years from Earth. At 99% of light speed, they are 62 years of ship time away. A traveler departing Earth at 25 would arrive at the Pleiades at 87, old perhaps by current standards, but within reach of lifespans that advancing medicine may make routine before the century ends. They would arrive at a cluster of hot blue stars, young by stellar standards at approximately 100 million years old, surrounded by wisps of nebulosity that the cluster is currently passing through interstellar gas, illuminated by the intense ultraviolet radiation of the cluster's brightest members. The famous blue haze visible in long-exposure photographs of the Pleiades from Earth is not a remnant of the cluster's formation. It is an unrelated cloud the cluster encountered in its journey around the galaxy lit from outside. From within the Pleiades, Earth's sun would be invisible to the naked eye. The distance back home would exceed the threshold at which stars of our sun's luminosity become too faint to detect without optical aid. The familiar constellations would have transformed completely their component stars, redistributed across the sky by the changed perspective. The traveler would stand or float in the light of unfamiliar suns surrounded by stars no human being has ever been close to, in a place where the night sky contains no reference point linking back to the world where they were born. Push velocity to 99.9% of light speed. Gamma now exceeds 22. 80 years of ship time corresponds to over 1760 years of Earth time. The same 80 years of biological experience carries a traveler approximately 1800 light-years from Earth. Within this radius, the nature of accessible destinations changes fundamentally. At 1800 light-years, you are no longer exploring the local stellar neighborhood, the comfortable region of the galaxy, where the density of stars and the character of the interstellar medium are broadly similar to what surrounds our own sun. You are beginning to encounter the large-scale structures of the galactic disk, star-forming regions of a scale and activity that dwarfs anything within a few hundred light-years of Earth. Clouds of gas and dust so massive that gravity is actively compressing them into new suns, some of which are already igniting and blowing away the material that formed them with the intensity of their radiation. The Orion Nebula, the most observed star-forming region in the northern sky, the object that sits in the sword of the familiar winter constellation and appears as a fuzzy patch to the naked eye and an intricate cathedral of gas and light through any telescope, lies approximately 1344 light-years from Earth. At 99.9% of light speed, a traveler reaches the Orion Nebula in just under 61 years of ship time, old enough to have lived a full adult life, young enough perhaps to spend years exploring. What they would find there is unlike anything in our solar neighborhood. The Orion Nebula is the nearest massive star-forming region to Earth, a cloud of hydrogen and dust, approximately 24 light-years across, containing enough material to form several thousand stars of solar mass. Within it, the trapezium cluster, 4 hot, massive, brutally luminous young stars, pours ultraviolet radiation into the surrounding gas, with such intensity that the hydrogen glows, excited to fluorescence by the energy pouring through it. This is the light we see from Earth. The nebula is not glowing of its own accord. It is being lit from within like a lantern by 4 extraordinarily energetic stars that formed perhaps 300,000 years ago, recently by stellar timescales from the same cloud of material that still surrounds them. Within the Orion Nebula, a traveler would witness star formation in progress. Protostars, dense knots of gas and dust that have not yet ignited nuclear fusion at their cores, are detectable throughout the cloud at various stages of collapse. Some are surrounded by protoplanetary disks, flat rotating structures of material that are actively assembling themselves into planetary systems. The same process that formed our own solar system 4.6 billion years ago is happening here now, in multiple locations simultaneously. A traveler in the Orion Nebula would be watching the birth of worlds. The radiation environment would be extraordinarily hostile by Earth standards. The trapezium stars emit ultraviolet radiation intense enough to ionize the surrounding nebula across distances of dozens of light-years. Any unshielded biological tissue exposed to this environment would be rapidly damaged. but a spacecraft with adequate shielding could navigate through the outer regions of the nebula, conducting observations of star formation that no Earth-based instrument could replicate, watching the accretion of planetary systems in real time, perhaps detecting in some of those forming systems the conditions that might, given billions of years of subsequent evolution, produce something like life. At 99.99% of light speed, gamma exceeds 70. 80 years of ship time spans over 5600 years of Earth time. The journey covers approximately 5600 light years, more than 5% of the diameter of the Milky Way. At this distance, the traveler is penetrating into regions of the galaxy that appear from Earth only as smeared light against the background of the Milky Way's central bar. Individual star systems are still individually identifiable, but the density of stars has increased substantially. The interstellar medium has grown somewhat denser, the radiation environment is more intense, and the scale of the structure's accessible star clusters containing hundreds of thousands of stars, massive, molecular. The Eta Carinae Nebula, one of the largest and most energetically active star-forming regions in the entire Milky Way, lies approximately 7500 light-years from Earth. At 99.99% of light speed, an 80-year journey falls just short of reaching it. A traveler would need approximately 107 years of ship time to complete the transit, but with modest life extension or a slightly higher velocity, the Carina Nebula enters reach. What awaits there is a stellar environment of almost grotesque intensity. The nebula extends across more than 300 light-years and contains some of the most massive and luminous stars known to exist, including Eta Carinae itself, a stellar system at the edge of stability, a star so massive that it periodically erupts, ejecting shells of material into the surrounding nebula that are visible from Earth as bright wisps against the dark clouds. Eta Carinae may explode as a hypernova within the next several thousand years, an event that would briefly outshine every other star in the galaxy from the perspective of Earth-based observers. Now consider the galactic center, 26,000 light-years from Earth. At the heart of the Milky Way, invisible from our position in the galaxy's disk because of the intervening dust and gas that absorbs virtually all optical and ultraviolet light, detectable only through infrared and radio observations that can penetrate the obscuring material, sits a gravitational monster, Sagittarius A star, a black hole containing approximately 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury, surrounded by dense star clusters where stars orbit the central mass at velocities of thousands of kilometers per second, surrounded by clouds of molecular gas, by streams of ionized hydrogen, by the remnants of stars torn apart by tidal forces as they ventured too close to the singularity. At 99.99% of light speed, reaching the galactic center requires approximately 370 years of ship time. Beyond a single lifetime, but perhaps within reach of a multi-generational crew, a vessel launched not with the expectation of any individual surviving to arrival, but with the commitment that the children and grandchildren of the original crew would arrive at the most remarkable destination in our galaxy. At 99.999% of light speed, gamma exceeds 223. 80 years of ship time now spans nearly 1,80000 years of Earth time. The journey covers approximately 1,80000 light years, 2/3 of the way across the galactic disk. The galactic center falls within an 80-year journey, barely for a traveler departing young and arriving old. They would spend the entire arc of their adult life in transit, departing as someone young enough to still believe in the possibility of everything, and arriving as someone old enough to know exactly what they have paid for the privilege. What would they find at the galactic center? The region surrounding Sagittarius A star is one of the most extreme environments in the Milky Way. Stars orbit the central black hole at velocities that would carry them from Earth to the Moon in seconds. The density of stars in the innermost parsec, roughly 3 light-years, exceeds anything in the galaxy's disk by a factor of millions. There is no night in the galactic center. The sky in every direction blazes with the light of thousands of nearby stars, the closest of them lying within light weeks rather than light years. Entire stellar systems pass close enough to the central black hole to have their outer regions stripped away by tidal forces, the material spiraling inward to join the accretion structures that periodically flare with energy when significant masses fall into the singularity. It is a place of violence and beauty at a scale our solar neighborhood cannot approximate. A traveler arriving there would experience a cosmos qualitatively different from anything any human being has ever seen. A sky ablaze with close stars, a central darkness pulling at everything around it, the fundamental architecture of a galaxy visible from its core in a way that no exterior vantage point can reveal. And yet even the galactic center is not the outer limit of what a single human life can reach at the most extreme velocities physics permits. At 99.9999% of light speed, gamma exceeds 700. 80 years of ship time corresponds to more than 56,000 years of Earth time. The journey covers over 56,000 light years, more than half the diameter of the Milky Way. The Large Magellanic Cloud, a satellite galaxy of the Milky Way orbiting at approximately 16,000 light years, requires roughly 228 years of ship time. At this velocity, again multi-generational, but perhaps reachable by a crew committed to the journey as a civilization-defining act rather than an individual adventure. Push gamma into the thousands and the arithmetic of cosmic distance begins to fracture in ways that strain the capacity to hold the meaning of the numbers in mind simultaneously with the meaning of a human life. At gamma equal to 100,000 achievable at velocities so close to light speed that the difference exists only as a mathematical abstraction. 80 years of ship time spans 8,000,000 years of Earth time. The journey covers 8,000,000 light years. The Andromeda Galaxy, the nearest major galaxy to the Milky Way, a spiral system containing approximately 1 trillion stars at a distance of 2.5 million light years, requires roughly 250 years of ship time. A committed crew of explorers, launching with the knowledge that no individual among them would survive to see arrival, could deliver their descendants to an entirely separate island universe, to a galaxy that has evolved independently of our own for billions of years, to a sky where the Milky Way appears as a faint smear of light, one galaxy, among many visible to the naked eye in every direction. What would those descendants find? Andromeda is larger than the Milky Way, containing roughly twice as many stars with a more prominent central bulge and a more massive central black hole. Estimated at 100 million solar masses, 25 times more massive than Sagittarius. A star. The galaxy hosts its own satellite system, its own star-forming regions, its own stellar populations ranging from ancient globular clusters formed in the earliest epochs of cosmic time to young open clusters still embedded in the molecular clouds that birthed them. Some fraction of Andromeda's trillion stars almost certainly host planets. Some fraction of those planets almost certainly orbit within habitable zones. Whether any of them harbor life, whether any of those worlds have produced something that looks at the sky and wonders, is a question that 2.5 million light-years of distance has so far placed beyond our ability to answer. A crew arriving in Andromeda would be, in the most literal sense possible, the first humans in an alien galaxy. Their home galaxy would be a faint patch of light in the Andromedan sky, indistinguishable to the naked eye from the hundreds of other galaxies visible in every direction. The specific star around which Earth orbits would be completely undetectable, lost in the undifferentiated glow of 400 billion stellar sources blurred together by distance into a single smear of pale luminosity. The thread connecting them to their origin would be real, but invisible, detectable only through instruments, meaningful only through memory and record, and the knowledge carried across generations and hundreds of years of transit that they came from somewhere specific, in that faint and unremarkable patch of light. This is the mathematics of a human lifetime at relativistic velocities. It is not a set of abstract numbers arranged to impress. It is a genuine accounting of what physics permits of what the universe actually offers to any being willing and able to move at the right speed. The costs are extraordinary. The energy required, the engineering demanded, the temporal isolation imposed. These are prices that dwarf anything humanity has ever paid for any achievement. But the universe is not withholding these destinations. It is not hiding them behind laws that forbid access. It is merely setting a price and waiting to see whether any civilization anywhere will eventually pay it. But the mathematics of an expanding universe introduces one final constraint, one that the equations of special relativity alone cannot reveal, and that changes the accounting in ways both sobering and urgent. Because the destinations described above are not stationary, they are moving, and the space between them and us is not static. It is growing continuously in every direction, driven by a force that was not even known to exist until 1998. The universe is not simply large, it is getting larger, and it is getting larger faster with every passing year. Begin with a single human life. 80 years. Not 80 years of rest and waiting, but 80 years of active experience, assumptions, of thought, of biological aging measured in heartbeats and cell divisions, and the slow accumulation of memory. 80 years is what most humans in the developed world can reasonably expect with modern medicine, with reasonable fortune, with no catastrophic interruption. It is not a long time by cosmic standards. It is not long by the standards of geology, or evolution, or the lifespan of stars. But it is what we have. It is the temporal budget each human being receives at birth, and the question before us now is what that budget can purchase when spent at the right velocity. The answer depends entirely on how fast you are willing to go. At 90% of light speed, gamma equals approximately 2.3. For every year that passes aboard that spacecraft, 2.3 years pass on Earth. An 80-year journey measured in ship time corresponds to roughly 184 years of Earth time. This velocity is already far beyond anything humanity has achieved, requiring propulsion technologies decades or centuries ahead of current capability. Yet in terms of what it permits, in terms of what destinations it unlocks, within a single human lifetime, 90% of light speed is almost conservative. At this velocity, 80 years of ship time carries a traveler approximately 73 light-years from Earth. The surrounding volume of space within 73 light-years contains roughly 2000 star systems. Among them are stars that astronomers have studied in detail from Earth. Tau Ceti, 11.9 light-years distant, a sun-like star with confirmed planetary companions, including at least one candidate in the habitable zone, Epsilon Eridani, 10.5 light-years away, younger than our Sun, still surrounded by a debris disk that may be coalescing into a mature planetary system, 61 Cygni, a binary system 11.4 light-years from Earth, the first star beyond our Sun to have its distance measured accurately achieved by German astronomer Friedrich Bessel in 1838, using the technique of stellar parallax. The apparent shift in a star's position as Earth moves from one side of its orbit to the other. Bessel spent months of careful observation to determine that 61 Cygni lay approximately 10 light-years away. He announced the result to the Berlin Academy in 1838 as one of the great achievements of observational astronomy. The star had been catalogued, named and studied for decades before anyone knew how far it was. Now we know it hosts two orange dwarf stars, orbiting each other gravitationally bound, with at least one confirmed planetary companion detected through the wobble these planets induce in their parent star's motion across the sky. At 90% of light speed, 61 Cygni lies less than 6 years of ship time from Earth. A traveler departing in their 20s would arrive in their early 30s, having crossed to a stellar system whose distance Bessel labored years to merely measure. They would find two suns in the sky, where we have one each smaller and cooler than our own, burning with a reddish-orange light that gives every surface a warmth unlike any illumination on Earth. Any planets in the habitable zone of this system receive a different quality of radiation than Earth does, cooler, redder, with different implications for any photosynthetic chemistry that might have emerged there. This is what 90% of light speed purchases within the first fraction of an 80-year journey, not the nearest star, not a single destination, a neighborhood. a volume of space containing 2,000 systems, dozens of which have been studied closely enough that we know something real about what exists there. But 90% is where we begin. The mathematics become genuinely extraordinary when velocity climbs higher. At 99% of light speed, gamma reaches 7.1. 80 years of ship time now corresponds to roughly 568 years of Earth time. More significantly, 80 years of ship time at this velocity carries a traveler approximately 570 light-years from Earth. The sphere of accessible space expands dramatically, not proportionally, but explosively. Where 90% of light speed enclosed a volume 73 light-years in radius, 99% encloses a sphere nearly 8 times larger in radius and more than 500 times larger in total volume. Within 570 light-years of Earth lies a cosmos that begins to look genuinely alien compared to our immediate stellar neighborhood. The Hyades cluster, the nearest open star cluster to our solar system, a loose grouping of several hundred stars sharing a common origin, lies approximately 153 light-years distant. At 99% of light speed, a traveler reaches the Hyades in roughly 22 years of ship time. They would find themselves surrounded by stars that formed together from the same molecular cloud, perhaps 625 million years ago. Stars that began their lives as siblings and have since drifted apart on slightly different trajectories through the galaxy. The Hyades contain stars at various stages of the stellar life cycle, from young blue-white stars burning hot and fast to older orange and red dwarf stars that will outlive the sun by billions of years. Studying a cluster like the Hyades from within, not from 153 light-years away through Earth's atmosphere and the intervening dust, but from among its constituent stars, would provide astronomical data of a quality no Earth-based or Earth-orbiting telescope could approach. The three-dimensional structure of the cluster, the precise motions of individual stars relative to their neighbors, the distribution of any planetary systems within the cluster's gravitational embrace, all of this would be accessible in a way that remote observation can never replicate. At 570 light-years, an 80-year journey at 99% of light speed reaches something that has captured human imagination since the first clear winter night any human being looked upward and noticed it. The Pleiades, the Seven Sisters, the star cluster that appears in the mythology of cultures separated by oceans and millennia, in Greek mythology as the daughters of Atlas and Pleione, transformed into stars by Zeus to spare them from the hunter Orion's pursuit. In Japanese culture, as Subaru, the word still used for the automaker, whose logo depicts the cluster's 6 brightest stars. In Aboriginal Australian traditions as the Makara, in Hindu astronomy as the Kritika, in the traditions of the Lakota people of North America. Virtually every culture that has ever looked at the winter sky has noticed the Pleiades, named them, woven stories around them. They lie approximately 440 light-years from Earth. At 99% of light speed, they are 62 years of ship time away. A traveler departing Earth at 25 would arrive at the Pleiades at 87, old, perhaps by current standards, but within reach of lifespans that advancing medicine may make routine before the century ends. They would arrive at a cluster of hot blue stars, young by stellar standards at approximately 100 million years old, surrounded by wisps of nebulosity that the cluster is currently passing through interstellar gas, illuminated by the intense ultraviolet radiation of the cluster's brightest members. The famous blue haze, visible in long-exposure photographs of the Pleiades from Earth, is not a remnant of the cluster's formation. It is an unrelated cloud, the cluster encountered in its journey around the galaxy lit from outside. From within the Pleiades, Earth's sun would be invisible to the naked eye. The distance back home would exceed the threshold at which stars of our sun's luminosity become too faint to detect without optical aid. The familiar constellations would have transformed completely, their component stars redistributed across the sky by the changed perspective. The traveler would stand or float in the light of unfamiliar suns surrounded by stars no human being has ever been close to, in a place where the night sky contains no reference point linking back to the world where they were born. push velocity to 99.9% of light speed. Gamma now exceeds 22. 80 years of ship time corresponds to over 1760 years of Earth time. The same 80 years of biological experience carries a traveler approximately 1800 light-years from Earth. Within this radius, the nature of accessible destinations changes fundamentally. At 1800 light-years, you are no longer exploring the local stellar neighborhood, the comfortable region of the galaxy, where the density of stars and the character of the interstellar medium are broadly similar to what surrounds our own sun. You are beginning to encounter the large-scale structures of the galactic disk, star-forming regions of a scale and activity that dwarfs anything within a few hundred light-years of Earth. Clouds of gas and dust so massive that gravity is actively compressing them into new suns, some of which are already igniting and blowing away the material that formed them with the intensity of their radiation. The Orion Nebula, the most observed star-forming region in the northern sky, the object that sits in the sword of the familiar winter constellation and appears as a fuzzy patch to the naked eye and an intricate cathedral of gas, light through any telescope lies approximately 1344 light-years from Earth. At 99.9% of light speed, a traveler reaches the Orion Nebula in just under 61 years of ship time, old enough to have lived a full adult life, young enough perhaps to spend years exploring. What they would find there is unlike anything in our solar neighborhood. The Orion Nebula is the nearest massive star-forming region to Earth, a cloud of hydrogen and dust, approximately 24 light-years across, containing enough material to form several thousand stars of solar mass. Within it, the trapezium cluster, 4 hot, massive, brutally luminous young stars, pours ultraviolet radiation into the surrounding gas with such intensity that the hydrogen glows, excited to fluorescence by the energy pouring through it. This is the light we see from Earth. The nebula is not glowing of its own accord. It is being lit from within like a lantern by 4 extraordinarily energetic stars that formed perhaps 3,000,000 years ago, recently by stellar timescales, from the same cloud of material that still surrounds them. Within the Orion Nebula, a traveler would witness star formation in progress. Protostars, dense knots of gas and dust that have not yet ignited nuclear fusion at their cores, are detectable throughout the cloud at various stages of collapse. Some are surrounded by protoplanetary disks, flat rotating structures of material that are actively assembling themselves into planetary systems. The same process that formed our own solar system 4.6 billion years ago is happening here now, in multiple locations simultaneously. A traveler in the Orion Nebula would be watching the birth of worlds. The radiation environment would be extraordinarily hostile by Earth standards. The trapezium stars emit ultraviolet radiation intense enough to ionize the surrounding nebula across distances of dozens of light-years. Any unshielded biological tissue exposed to this environment would be rapidly damaged, but a spacecraft with adequate shielding could navigate through the outer regions of the nebula, conducting observations of star formation that no Earth-based instrument could replicate, watching the accretion of planetary systems in real time, perhaps detecting in some of those forming systems the conditions that might, given billions of years of subsequent evolution, produce something like life. At 99.99% of light speed, gamma exceeds 70. 80 years of ship time spans over 5600 years of Earth time. The journey covers approximately 5600 light-years, more than 5% of the diameter of the Milky Way. At this distance, the traveler is penetrating into regions of the galaxy that appear from Earth only as smeared light against the background of the Milky Way's central bar. Individual star systems are still individually identifiable, but the density of stars has increased substantially. The interstellar medium has grown somewhat denser, the radiation environment is more intense, and the scale of the structures accessible star clusters containing hundreds of thousands of stars, massive molecular clouds stretching across hundreds of light-years, supernova remnants expanding outward from the depths of massive stars, has grown to proportions that our immediate cosmic neighborhood cannot match. The Eta Carini Nebula, one of the largest and most energetically active star-forming regions in the entire Milky Way, lies approximately 7,500 light-years from Earth. At 99.99% of light speed, an 80-year journey falls just short of reaching it. A traveler would need approximately 107 years of ship time to complete the transit. But with modest life extension or a slightly higher velocity, the Carina Nebula enters reach. What awaits there is a stellar environment of almost grotesque intensity. The nebula extends across more than 300 light-years and contains some of the most massive and luminous stars known to exist, including Eta Carinae itself, a stellar system at the edge of stability, a star so massive that it periodically erupts, ejecting shells of material into the surrounding nebula that are visible from Earth as bright wisps against the dark clouds. Eta Carinae may explode as a hypernova within the next several thousand years, an event that would briefly outshine every other star in the galaxy from the perspective of Earth-based observers. Now, consider the galactic center, 26,000 light-years from Earth. At the heart of the Milky Way, invisible from our position in the galaxy's disk because of the intervening dust and gas that absorbs virtually all optical and ultraviolet light, detectable only through infrared and radio observations that can penetrate the obscuring material, sits a gravitational monster, Sagittarius A star, a black hole containing approximately 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury, surrounded by dense star clusters where stars orbit the central mass at velocities of thousands of kilometers per second, surrounded by clouds of molecular gas, by streams of ionized hydrogen, by the remnants of stars torn apart by tidal forces as they ventured too close to the singularity. At 99.99% of light speed, reaching the galactic center requires approximately 370 years of ship time, beyond a single lifetime, but perhaps within reach of a multi-generational crew, a vessel launched not with the expectation of any individual surviving to arrival, but with the commitment that the children and grandchildren of the original crew would arrive at the most remarkable destination in our galaxy. At 99.999% of light speed, Gamma exceeds 223. 80 years of ship time now spans nearly 18,000 years of Earth time. The journey covers approximately 18,000 light-years, 2/3 of the way across the galactic disk. The galactic center falls within an 80-year journey, barely for a traveler departing young and arriving old. They would spend the entire arc of their adult life in transit, departing as someone young enough to still believe in the possibility of everything, and arriving as someone old enough to know exactly what they have paid for the privilege. What would they find at the galactic center? The region surrounding Sagittarius A star is one of the most extreme environments in the Milky Way. Stars orbit the central black hole at velocities that would carry them from Earth to the Moon in seconds. The density of stars in the innermost parsec, roughly 3 light-years, exceeds anything in the galaxy's disk by a factor of millions. There is no night in the galactic center. The sky in every direction blazes with the light of thousands of nearby stars, the closest of them lying within light weeks rather than light years. Entire stellar systems pass close enough to the central black hole to have their outer regions stripped away by tidal forces, the material spiraling inward to join the accretion structures that periodically flare with energy when significant masses fall into the singularity. It is a place of violence and beauty at a scale our solar neighborhood cannot approximate. A traveler arriving there would experience a cosmos qualitatively different from anything any human being has ever seen. A sky ablaze with close stars, a central darkness pulling at everything around it, the fundamental architecture of a galaxy visible from its core in a way that no exterior vantage point can reveal. And yet even the galactic center is not the outer limit of what a single human life can reach at the most extreme velocities physics permits. At 99.9999% of light speed, Gamma exceeds 700. 80 years of ship time corresponds to more than 5,600,000 years of Earth time. The journey covers over 5,600,000 light years, more than half the diameter of the Milky Way. The Large Magellanic Cloud, a satellite galaxy of the Milky Way orbiting at approximately 1,600,000 light-years, requires roughly 228 years of ship time. At this velocity again, multi-generational, but perhaps reachable by a crew committed to the journey as a civilization-defining act rather than an individual adventure. Push gamma into the thousands, and the arithmetic of cosmic distance begins to fracture in ways that strain the capacity to hold the meaning of the numbers in mind simultaneously with the meaning of a human life. At gamma equal to 1,000,000, achievable at velocities so close to light speed that the difference exists only as a mathematical abstraction. 80 years of ship time spans 8,000,000 years of Earth time. The journey covers 8,000,000 light-years. The Andromeda Galaxy, the nearest major galaxy to the Milky Way, a spiral system containing approximately 1 trillion stars at a distance of 2.5 million light-years, requires roughly 250 years of ship time. A committed crew of explorers, launching with the knowledge that no individual among them would survive to see arrival, could deliver their descendants to an entirely separate island universe, to a galaxy that has evolved independently of our own for billions of years, to a sky where the Milky Way appears as a faint smear of light, one galaxy among many visible to the naked eye in every direction. What would those descendants find? Andromeda is larger than the Milky Way, containing roughly twice as many stars, with a more prominent central bulge and a more massive central black hole estimated at 100 million solar masses, 25 times more massive than Sagittarius. A star. The galaxy hosts its own satellite system, its own star-forming regions, its own stellar populations ranging from ancient globular clusters formed in the earliest epochs of cosmic time to young open clusters still embedded in the molecular clouds that birthed them. Some fraction of Andromeda's trillion stars almost certainly host planets. Some fraction of those planets almost certainly orbit within habitable zones. Whether any of them harbor life, whether any of those worlds have produced something that looks at the sky and wonders, is a question that 2.5 million light-years of distance has so far placed beyond our ability to answer. A crew arriving in Andromeda would be in the most literal sense possible the first humans in an alien galaxy. Their home galaxy would be a faint patch of light in the Andromedan sky, indistinguishable to the naked eye from the hundreds of other galaxies visible in every direction. The specific star around which Earth orbits would be completely undetectable, lost in the undifferentiated glow of 400 billion stellar sources, blurred together by distance into a single smear of pale luminosity. The thread connecting them to their origin would be real but invisible, detectable only through instruments, meaningful only through memory and record, and the knowledge carried across generations and hundreds of years of transit that they came from somewhere specific in that faint and unremarkable patch of light. This is the mathematics of a human lifetime at relativistic velocities. It is not a set of abstract numbers arranged to impress. It is a genuine accounting of what physics permits, of what the universe actually offers to any being willing and able to move at the right speed. The costs are extraordinary. The energy required, the engineering demanded, the temporal isolation imposed. These are prices that dwarf anything humanity has ever paid for any achievement. But the universe is not withholding these destinations. It is not hiding them behind laws that forbid access. It is merely setting a price and waiting to see whether any civilization anywhere will eventually pay it. But the mathematics of an expanding universe introduces one final constraint, one that the equations of special relativity alone cannot reveal, and that changes the accounting in ways both sobering and urgent. Because the destinations described above are not stationary. They are moving, and the space between them and us is not static. It is growing continuously in every direction, driven by a force that was not even known to exist until 1998. The universe is not simply large, it is getting larger. And it is getting larger, faster, with every passing year. Phần 5, 7 hoàn thành. Số từ phần này 2580 từ tổng tích lũy, 11990 từ phần tiếp theo. Phần 6D Expanding. Prison sẽ đi vào Dark Energy Hubble Sphere, Cosmological Event Horizon, và sự thật rằng cửa sổ khám phá vũ trụ đang đóng lại từng ngày. Những thiên hà ta thấy hôm nay đang dần biến mất khỏi tầm với không phải trong tương lai xa, mà theo thang vũ trụ gần hơn ta nghĩ. Nói ok để tiếp tục. Ok 1431. In 1998, two independent teams of astronomers were studying the light from distant supernovae stellar explosions, so luminous that a single dying star briefly outshines its entire host galaxy, visible across billions of light years of cosmic space. These explosions, called Type Ia supernovae, occur when a white dwarf star in a binary system accretes enough material from its companion to trigger a runaway nuclear detonation. Because the conditions triggering this detonation are highly uniform across different events, the resulting explosions produce nearly identical peak luminosities. They function as what astronomers call standard candles objects of known intrinsic brightness, whose distance can be calculated by comparing how bright they appear from Earth against how bright they are known to be. The two teams, one led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rees, were using these supernovae to measure how the expansion of the universe has changed over cosmic time. The expectation shared by virtually every cosmologist working in the field was that the expansion should be slowing down. Gravity acting across cosmic scales should be pulling matter back toward itself, gradually decelerating the outward rush that began at the Big Bang. The supernovae data would quantify this deceleration, revealing whether the universe would eventually collapse back on itself or coast forever outward at diminishing speed. What the data showed instead shattered the expectation entirely. The distant supernovae were fainter than they should have been, fainter than any decelerating expansion could explain. They were farther away than predicted. The universe was not slowing down, it was speeding up. The expansion of space was accelerating, driven by something that existed in the vacuum of space itself, a form of energy density that does not dilute, as space expands, that does not cluster around matter that pervades every cubic centimeter of the cosmos with uniform pressure, pushing space apart from within. This discovery earned the 2011 Nobel Prize in Physics for Perlmutter, Schmidt, and Rees. It revealed that approximately 68% of the total energy content of the observable universe consists of this mysterious component now called dark energy, whose nature remains one of the deepest unsolved problems in all of physics. The remaining 32% consists of matter, both the ordinary matter composing stars, planets, and every object ever directly observed, and the dark matter whose gravitational effects are visible throughout the cosmos, but whose constituent particles have never been directly detected. Dark energy does not interact with matter in any way that has been observed. It does not cluster, it does not decay, it does not respond to any force except gravity, which it appears to resist through its negative pressure, a property that in the framework of general relativity produces a repulsive gravitational effect, accelerating the expansion of space rather than decelerating it. The simplest mathematical description of dark energy, called the cosmological constant, was originally introduced by Einstein himself in 1917 as a fudge factor to produce a static universe, then abandoned after Edwin Hubble's 1929 discovery of cosmic expansion, which Einstein reportedly called the greatest blunder of his life. The cosmological constant returned from the discarded heap of physics history in 1998, vindicated by the supernova observations, now recognized not as a blunder, but as a genuine feature of space-time that Einstein had accidentally stumbled upon decades before observational confirmation. The consequences of accelerating expansion for any would-be cosmic explorer are as profound as they are merciless. Consider first the Hubble sphere. This is not a physical object or a boundary marked by any observable phenomenon. It is a mathematical surface defined by a specific relationship between distance and recession velocity. The universe expands in such a way that every point in space moves away from every other point with the recession velocity between any 2 points proportional to the distance between them. Double the distance and you double the recession velocity. This relationship, described by the Hubble constant, means that at some specific distance from any observer, the recession velocity equals the speed of light. That distance, currently approximately 14.4 billion light-years from Earth, defines the Hubble sphere. Galaxies at this distance recede from us at exactly 1.86282 miles per second. Galaxies beyond this boundary recede faster than light. This does not violate special relativity because the galaxies are not moving through space at superluminal velocities. Space itself is expanding, carrying the galaxies along. The distinction is physically real and important, but it offers no comfort to a traveler attempting to reach those galaxies. Whether a galaxy recedes because it is moving through space faster than light, or because the space between it and the observer is expanding faster than light can cross it, the practical result is identical. A signal sent towards such a galaxy, or a spacecraft accelerating toward it at any velocity below light speed, faces an expanding gulf that grows faster than the signal or spacecraft can close it. The message never arrives. The spacecraft never reaches its destination. Yet the Hubble sphere is not the ultimate boundary. Here, the distinction between light and a spacecraft becomes important in a way that offers a narrow but genuine advantage to the traveler. A photon emitted from Earth today toward a galaxy just beyond the Hubble sphere faces immediate defeat. It travels at light speed and cannot accelerate. The expanding space ahead of it grows faster than it can cross. The photon will travel forever, through an eternally expanding void, never reaching the galaxy it was aimed at. A spacecraft can accelerate. It can in principle start slowly and build velocity as it travels, pushing outward with enough thrust to stay ahead of the local expansion rate at its current position. By doing so, it can penetrate into regions beyond the current Hubble sphere, regions where light emitted today from Earth could never reach. This is not a loophole in the expansion. It is a consequence of the fact that the Hubble sphere itself moves outward as the universe expands, and a spacecraft accelerating continuously can chase that moving boundary. But the cosmological event horizon closes this avenue with finality. The event horizon is not a fixed surface. It is a boundary defined by integration over the entire future history of cosmic expansion, a calculation of how far any signal or spacecraft departing Earth today can possibly reach given unlimited time, unlimited velocity, and the full future trajectory of dark energy's influence on the expansion of space. Currently, this boundary lies approximately 16 to 17 billion light-years from Earth. Beyond this horizon, no departure from Earth today can ever arrive. It does not matter how fast the spacecraft travels. It does not matter how long it continues. Dark energy will carry those destinations outward faster than any approach can compensate. The destinations beyond the event horizon are not merely difficult to reach, they are permanently, absolutely, irrevocably inaccessible to anything departing from our location in space and time. The 2 trillion galaxies estimated to populate the observable universe, the full sensors of cosmic structure visible to our most powerful telescopes, are almost entirely beyond this horizon. The observable universe extends 46.5 billion light-years in every direction. The event horizon encompasses only 16 to 17 billion light-years. The overwhelming majority of everything we can see is already beyond any possibility of physical contact. We observe those distant galaxies as they were billions of years ago when the light now reaching our telescopes began its journey. But we can never touch them. We can never send a probe that arrives. We can never receive a response to any signal. They exist in our sky as images, ancient light painting, pictures of places that have been beyond reach since long before our planet formed, and that grow more inaccessible with each passing second as dark energy accelerates their recession. The event horizon also shrinks over time in a manner that creates a genuine and urgent countdown for cosmic exploration. This is the feature of dark energy that receives the least attention in popular accounts of cosmology and deserves considerably more. As the expansion of the universe accelerates the region of space from which any signal departing today can ever reach us, our future light cone in the language of space-time geometry contracts, galaxies that lie within the event horizon today that are in principle still reachable by a sufficiently fast spacecraft departing now, will cross beyond that horizon in the future as accelerating expansion carries them outward faster than any approach can compensate. The Virgo cluster, a massive aggregation of more than 1,300 galaxies, approximately 54 million light-years from Earth. The gravitational center of the local supercluster, to which the Milky Way belongs currently, lies well within the event horizon and is in principle reachable. But dark energy is carrying it outward. Within a finite future time, measurable in billions of years, the Virgo cluster will cross beyond the event horizon and become permanently inaccessible. The window for reaching it is open today. It will not remain open indefinitely. On timescales of tens of billions of years long by human standards, relatively modest by cosmic ones, the event horizon will have contracted to encompass only what cosmologists call the local group. This is the gravitationally bound collection of galaxies in our immediate cosmic neighborhood, the Milky Way, Andromeda, the Triangulum Galaxy, and approximately 50 smaller satellite and dwarf galaxies. These objects are gravitationally bound to one another, meaning they will not be carried apart by cosmic expansion, regardless of how aggressively dark energy acts on the space between them and everything else. Gravity holds them together against the expanding tide. Every other galaxy in the observable universe will have crossed permanently beyond the event horizon. The great clusters, the superclusters, the cosmic filaments connecting galaxies across hundreds of millions of light-years, all of it will recede beyond contact, visible for a time as increasingly redshifted light, and then eventually not even visible. The cosmic microwave background radiation, the thermal remnant of the Big Bang itself, the faint glow of microwave radiation filling the sky in every direction that represents our oldest direct observational evidence of the universe's origin, will redshift beyond any conceivable detection threshold. Its photons, already stretched to wavelengths centimeters long by 13 billion years of cosmic expansion, will stretch further and further until no instrument imaginable could register them. The observational signature of the Big Bang will vanish from the sky. Future astronomers inhabiting whatever merged galaxy descends from the collision of the Milky Way and Andromeda, a collision that is actually already underway, with the two galaxies approaching each other at approximately 70 miles per second and expected to begin their first interpenetration in roughly 4.5 billion years, will look outward at a sky empty of external galaxies. They will observe only their own merged system surrounded by the void. The evidence for cosmic expansion, for the existence of other galaxies, for the Big Bang itself, will have been erased by the very expansion that generated that evidence. These astronomers might develop physics from first principles and conclude from everything their instruments can detect that their galaxy constitutes the entirety of the universe. They would be wrong, but they would have no means of knowing it. Every photon that could have told them otherwise will have receded beyond the horizon before their civilization arose to ask the question. This future isolation gives the present moment a character that is difficult to fully absorb. We exist at a rare and genuinely privileged time in cosmic history, a window during which the evidence for the universe's true nature remains accessible, during which the grandeur of the cosmic structure is visible to any instrument capable of detecting it, during which the galaxies and clusters and filaments that define the large-scale architecture of everything are still technically reachable. That window is closing. Not tomorrow, not within any human-relevant time frame in the immediate sense, but it is closing. The universe's generosity with its own visibility is finite, and the clock measuring that generosity has been running since the first moment dark energy began its accelerating work. The practical implications for cosmic exploration are both clarifying and sobering. Of the 2 trillion galaxies currently within our observable universe, the fraction that lies within the cosmological event horizon within the region technically accessible to a spacecraft departing today at any velocity below light speed amounts to perhaps a few percent. The Virgo supercluster and a modest surrounding volume represents the realistic outer boundary of the reachable cosmos for any civilization located where we are. Beyond this boundary, the universe presents itself only a spectacle, an image on a cosmic screen that can be watched but never visited. The Perseus cluster 240 million light-years distant, the Coma cluster 320 million light-years away, the Great Wall of Galaxies extending across 500 million light-years that astronomers call the Sloan Great Wall, the Hercules Corona Borealis Great Wall, a structure so enormous it stretches across 10 billion light-years and challenges the theoretical expectation that the universe should appear homogeneous at the largest scales. These structures can be observed, they cannot be reached. They exist on the far side of a boundary that no propulsion system, no matter how advanced, can help any traveler cross. The event horizon, unlike the Hubble sphere, is not a boundary that can be outrun by accelerating hard enough. It is not a boundary set by our current technology. It is a boundary set by the geometry of space-time in an accelerating universe, an absolute limit on where the future can connect to the present from our specific location in cosmic history. And yet within that boundary, within the 16 to 17 billion light-years, still technically accessible, lies a volume of space containing hundreds of billions of galaxies, hundreds of billions of island universes, each containing hundreds of billions of stars, each potentially harboring planetary systems, biospheres, civilizations. The fraction of the cosmos accessible to us, though a small percentage of what we can observe, remains incomprehensible in its actual scale. We are not being offered a small room in a vast palace. We are being offered a palace and told with appropriate cosmic honesty that we cannot have the continent surrounding it. The event horizon creates something else that deserves careful reflection, an urgency to exploration that the static cosmos of earlier physics did not imply. If the universe were not expanding or expanding at a constant rate without acceleration, the galaxies visible today would remain accessible indefinitely. There would be no countdown, no closing window. A civilization could take its time, develop its propulsion technology across millennia, perfect its engineering across geological timescales, and still reach any galaxy in the observable universe without urgency. Dark energy removes this comfort. Every galaxy currently accessible will eventually cross beyond reach. The Virgo cluster's window closes first on cosmic timescales, then other nearby clusters, then the entire structure of the observable universe outside the local group. The destinations are finite. The time available to reach them is finite. The universe is running an auction in which the lots are galaxies, the currency is velocity, and the bidding closes on a schedule set by the physics of vacuum energy that no negotiation can alter. This is the context within which the question of how far a human can travel in one lifetime must ultimately be situated. Not a static backdrop of fixed distances and stable destinations, but a dynamic, expanding, accelerating cosmos in which the accessible fraction of total cosmic content decreases with each passing era, and in which the decisions made by any civilization about whether and when to develop interstellar propulsion carry consequences that extend across billions of years of future cosmic history. The universe does not wait. It has never waited. The expansion that began at the Big Bang has been carrying structure outward since the first moments of cosmic time, and the acceleration introduced by dark energy has been compounding that recession for the past several billion years. The window for exploring a cosmos that looks as rich and reachable as the one visible from Earth tonight is open now. It will not be open at this breadth forever. What remains is the most personal question of all. Not what physics permits, not what engineering might achieve, but what a traveler actually chooses what it means to reach for the stars when reaching means leaving everything behind, when the journey outward is also inescapably a journey away from every connection that makes the destination worth reaching for. There is a thought experiment that no physics textbook includes because it belongs not to the domain of calculation but to the domain of human experience. Imagine that the engineering problems have been solved, the propulsion technology exists, the spacecraft is built, the velocity is achievable. Everything that stood between a human being and the stars has been resolved by the accumulated effort of generations of scientists and engineers and the sustained commitment of a civilization that decided at some point in its history this mattered enough to pursue regardless of the cost. You are standing at the threshold of departure. Behind you is everything you have ever known, the particular quality of afternoon light in the place where you grew up, the sound of rain on a specific window, the faces of people whose expressions you can read without words, whose voices carry information in their timbre that no recording has ever quite captured. The accumulated texture of a life lived in a specific place at a specific time among specific people. The irreducible particularity of having been one human being rather than another, embedded in one moment of history rather than another, connected to one set of relationships rather than any other possible set. Ahead of you is the cosmos. The decision to step forward is not merely an engineering achievement. It is not merely a scientific accomplishment. It is a choice about what matters most, about whether the knowledge gained at the destination justifies the permanent severance from everything left behind. And, at the velocities necessary for meaningful relativistic travel, that severance is not metaphorical. It is not the ordinary grief of departure that every explorer in human history has experienced, and that every returning explorer has eventually resolved by coming home. It is something categorically different, something for which human experience has not yet developed adequate language. A traveler departing Earth at 99% of light speed toward the Pleiades cluster 440 light-years distant would experience the outward journey as lasting approximately 63 years. They would arrive old if they arrived at all, their biological age advanced by 6 decades of continuous existence inside a vessel that the universe treated as almost stationary in time, even as it crossed nearly 500,000 light-years of space. During those 63 years of ship time, Earth would have aged 444 years. Everyone the traveler had ever known would be dead. Not recently dead, dead for centuries. Their children, if they had any, would be long gone. Their grandchildren, their great-grandchildren. The institutions that structured their life, the governments, the universities, the cultural forms, the languages, even would have transformed beyond recognition across 4.5 centuries of continuous historical change. If the traveler turned around immediately upon arrival and began the return journey, they would reach Earth having aged approximately 126 years, while Earth aged nearly 900. They would return to a world separated from their departure by nearly a millennium. Whatever awaited them would share physical coordinates with the place they left, but essentially nothing else. The language spoken in the streets might be as different from the language of their departure as modern English is from the English of Geoffrey Chaucer. The political entities, the cultural references, the technological landscape, the very conception of what it means to be human, all of this could have changed so thoroughly across 900 years that the returning traveler would be in every meaningful sense a visitor from antiquity rather than a person coming home. This is not speculation. This is the arithmetic of time dilation applied to human relationships. It is what the equations actually demand of any traveler who chooses velocities high enough to make the stars accessible within a single lifetime. The early navigators who sailed beyond the horizon, Magellan circumnavigating the globe, Cook mapping the Pacific, the Norse settlers who reached North America 5 centuries before Columbus, all of them experienced the severance of departure. All of them left behind people and places they might never see again, accepting the possibility of permanent loss as the price of exploration. Some of them paid that price. Magellan died in the Philippines. Many of Cook's crew did not return. The Norse settlements in Vinland were eventually abandoned their survivors, recrossing the Atlantic to homes that had continued without them. But all of these departures maintained a connection to the era of origin. Letters could be written and eventually delivered. Returning sailors brought news that, however delayed, still described a world recognizable to those who had remained. The fabric of shared history, shared time, shared human experience persisted across the distance. A sailor gone for 3 years returned to a world 3 years older, changed in the ways that 3 years change things, but continuous with the world of departure. Relativistic travel severs this continuity absolutely. The traveler does not return to a world that has moved forward in the ordinary way. They return to a world that has undergone historical transformation on the scale of civilizations rising and falling, of technologies emerging from unrecognizable origins and developing into forms that the departed could not have anticipated. The connection between the traveler and their point of origin is maintained only by records, by the fact that somewhere in the historical archive of the civilization that launched them their name appears. Their departure is noted. Existence at a specific moment in time is documented. But the living connection, the experiential continuity, the shared history with people who remember them, this is gone. replaced by a gap so wide it encompasses centuries. For one-way travelers, those who depart without any intention of returning, who accept the nature of the journey as a permanent migration rather than an expedition, the severance is even more complete and in a strange way more honest. They are not pretending that a return is possible. They are not calculating what will remain of their world upon an eventual homecoming. They are choosing the destination over the origin, the unknown over the known, the future over the past, with full knowledge of what each choice means. Such travelers would become, in the most literal sense, the seeds of something new. A human presence planted in foreign soil, disconnected from the root system that produced it, dependent entirely on whatever they carry within themselves, their knowledge, their values, their biological nature, their memories of a world that will never exist again in any form accessible to them. They would arrive at their destination as the sole representatives of a civilization that has, from their perspective, simply ended. Not destroyed, still existing somewhere across the light years, still generating history and culture and knowledge, but ended for them as completely as if it had never been, because no bridge connects their present to its continuation. What would sustain such a traveler? What would make the journey worthwhile in terms that reach beyond the abstract value of expanding human knowledge into new regions of the cosmos? The answer may lie in something that every explorer in human history has carried regardless of the scale of their voyage: the act of witnessing, the particular and irreplaceable experience of being present at a place that no one from your origin has ever stood, of seeing with eyes that have crossed whatever distance separates you from everything familiar. Columbus on the beaches of the Caribbean, whatever his many failures as a human being, stood in a place where no European had ever stood, and looked at a world that European consciousness had not previously known existed. The experience of that witnessing, of being the first human being from a particular tradition to perceive a particular reality, carries a weight that is not diminished by subsequent discovery, subsequent colonization, subsequent historical complexity. A traveler arriving at the Pleiades, standing in the light of blue-white stars that no human being has ever been close to, looking back toward a sky where the sun is invisible and the constellations have shifted beyond recognition, would to be witnessing something that no human consciousness has ever witnessed. Not in a documentary, not through a telescope, not through data transmitted by a robotic probe, in person. With eyes evolved on a small planet orbiting an average star in an unremarkable corner of the galaxy, now adapted by circumstance to perceive light from stars 100 times more luminous than anything in our solar neighborhood. That witnessing has value. It has value that is difficult to quantify and impossible to fully communicate to anyone who was not present. It is the value of direct experience of reality apprehended without mediation of the cosmos encountered, rather than merely observed. And it is value that the universe appears to have made available through the mechanism of time dilation to any traveler willing and able to pay the price. The price is not measured only in energy. It is not measured only in engineering complexity or the decades of political will required to develop the necessary technology. The deepest price, the one that cannot be calculated or subsidized or shared, is paid in the currency of human connection. Every year gained through time dilation is a year subtracted from the shared experience of the civilization that launched the traveler. Every light year crossed is a corresponding stretch of temporal distance from the world of origin. The faster you go, the farther you can reach, and the more completely you leave behind every specific human relationship that gave your particular life its particular texture. This is not a reason not to go. It is simply the truth of what going costs. There is another dimension to this reckoning that the physics alone does not capture, and it concerns not the travelers who depart, but the civilization that remains. Every relativistic mission launched represents an investment of resources, of technological development, of the accumulated knowledge that makes such missions possible, that must be sustained across timescales longer than individual human lives. The engineers who design the propulsion system will not live to see the spacecraft reach its destination. The scientists who define the mission objectives will not receive the data their instruments collect. The civilization that launches a ship toward a star 440 light-years away commits to a relationship with that mission spanning centuries, maintained not by any individual, but by institutions, and cultural values, and the persistent sense that what was begun deserves to be continued. Human institutions have rarely demonstrated this kind of multi-generational commitment. The cathedrals of medieval Europe were built across centuries, with workers who laid foundations knowing they would never see the spires rise. But cathedrals served immediate social and spiritual functions throughout their construction, generating meaning and community and religious practice even in their unfinished states. An interstellar mission generates no intermediate returns. It produces data only at arrival centuries after departure. The civilization that sustains it must value the eventual result more than any intermediate benefit that the same resources might purchase. Whether any civilization, including our own, can maintain this kind of commitment across the relevant timescales is genuinely uncertain. Human history does not offer many encouraging examples of sustained purpose, outlasting the generations that originally held it. Empires fall. Technologies are lost. The knowledge of how to build certain medieval cathedrals was genuinely lost after the Gothic period. Later, restorers had to rediscover techniques that their predecessors had mastered. There is no guarantee that a civilization capable of launching an interstellar mission in 1 century would still be capable of receiving and interpreting its data in the next. Yet the alternative remaining within the solar system, exploring only what can be reached without relativistic velocities, accepting the horizon imposed by current propulsion technology as a permanent ceiling, carries its own cost. A civilization that chooses never to attempt the crossing is a civilization that has decided consciously or by default that the universe beyond a certain distance does not matter, that the 2 trillion galaxies visible through our telescopes are only images, only data, only knowledge of a distant kind, and that the possibility of presence of actual human experience in those remote places is not worth the price. That decision may be right. There are arguments for it that deserve honest consideration. The resources required for relativistic propulsion development deployed instead toward terrestrial problems, toward the elimination of poverty and disease and the environmental challenges that threaten the habitability of the only world humanity currently occupies, might produce more human benefit per unit of investment than any conceivable space exploration program. A civilization that cannot sustainably inhabit its home planet has no business launching ships toward other stars. The hierarchy of urgency that places survival above exploration is not obviously wrong, but it is also not obviously complete. Survival for what purpose? Continuation toward what destination? The question of what humanity is ultimately for, what the existence of a species capable of measuring the universe and contemplating its own place within it is ultimately service of, does not have an answer that the immediate calculus of resource allocation can supply. It is a question about meaning, and meaning does not resolve to an optimization problem. The universe exists. It is extraordinarily large. It contains extraordinary things. It has produced in at least one location beings capable of perceiving its scale and being moved by what they perceive. Whether those beings will ever stand in the light of another star, or gaze from within the Orion Nebula at the birth of new suns, or cross the void between galaxies and look back at the Milky Way as an external observer for the first time, these outcomes are not guaranteed. They may never occur. The engineering may prove permanently beyond reach. The political will may never coalesce. The window of cosmic accessibility may close before any civilization anywhere develops the technology to exploit it. But the physics does not forbid it. This is the central, irreducible fact that everything in this account has been building toward. The universe does not have a law that prevents human beings from reaching the stars. It has a price. An enormous, demanding, generation-spanning, personally devastating price that includes everything from the energy cost of acceleration to the temporal exile of relativistic travel to the severing of every human connection that gave the traveler's original life its specific weight and texture. But not a prohibition, a price. And prices, unlike prohibitions, can be paid. You exist at a specific moment in the history of a species that has existed for approximately 3,000,000 years on a planet orbiting a star that has burned for 4.6 billion years in a galaxy that formed roughly 13.6 billion years ago, in a universe that began as best our instruments and mathematics can determine approximately 13.8 billion years ago. You are made of atoms forged in the cores of stars that lived and died before our sun existed. The carbon in your cells was assembled in red giants. The iron in your blood was scattered by supernovae. You are, in the most literal chemical sense, a piece of the cosmos that has become aware of the cosmos matter that has organized itself into a form capable of measuring the universe and being astonished by what the measurement reveals. From your position on this small world, you can look outward and see 46.5 billion light-years in every direction. You can detect the afterglow of the Big Bang. You can measure the expansion rate of space. You can calculate the mass of black holes a billion light-years away from the ripples their collisions send through the fabric of space-time. You can determine from the wobble of distant stars the presence of planets you cannot see, and from the chemistry of the light those planets reflect, something of the composition of their atmospheres. You can do all of this without leaving the surface of the planet where you were born, and you can know with mathematical certainty that if you could move fast enough, if the engineering problems that currently prevent it were somehow resolved, you could cross distances that would bring you within a single lifetime of personal experience to places that the light now entering your eyes left before your species existed. You could travel to stellar nurseries where new suns are being born. You could stand in the light of stars that human mythology named thousands of years ago and that no human being has ever been close to. You could witness if the most extreme velocities are ever achieved a galaxy other than the one in which every human being who has ever lived was born. The universe has made this available, not easily, not cheaply, not without costs that reach into the deepest structures of human experience and demand things that no list of engineering specifications can capture, but available. The loophole is real. The mathematics is verified. The physics does not foreclose the possibility. What forecloses it, if it is ever foreclosed, will be something else entirely, a failure of imagination, a failure of will, a decision made by default rather than deliberation that the price is too high and the destination not worth what the journey costs, or it will not be foreclosed. Perhaps some generations separated from this one by decades or centuries of accumulated capability will look at the same equations that Einstein derived in a patent office in Bern in 1905 and see in them not the complexity of an unsolved engineering problem, but the clarity of a solved physics problem. The universe has told us what it costs to reach the stars. It has been telling us for over 100 years, in the language of mathematics, with a precision that admits no ambiguity. The stars are not impossibly distant, they are merely expensive. And the universe, indifferent to whether we ever pay the price or not, will continue expanding, will continue burning, will continue producing in its various corners. The extraordinary phenomena that time dilation could carry human consciousness to witness whether or not any human consciousness ever arrives to witness them. That is the final truth this account has been building toward. The universe does not need us to explore it. It existed for 9 billion years before our planet formed. It will exist for trillions of years after the last star has exhausted its fuel and gone cold. The extraordinary things within it, the star-forming nebulae, the galactic centers, the colliding galaxies, the phenomena that dwarf anything in our solar neighborhood, all of these will continue, whether or not any being capable of appreciation ever stands close enough to perceive them directly. But we are here, now, in the narrow window of cosmic time when the universe is still young enough to contain stars, still structured enough to contain the complexity that life requires, still observable enough that its history can be read in the light arriving from every direction. We are here with minds capable of measuring it, with mathematics capable of describing it, with imaginations capable of being moved by the scale of what the measurements reveal. And the equations say we could go there, not easily, not soon, not without paying a price that would cost us things we cannot fully anticipate until we are standing at the threshold of departure, looking back at everything we are leaving behind. But there, that single word contains everything. The difference between a universe that is only known and a universe that is also experienced. between a cosmos that exists in data and a cosmos that exists in presence, between looking at the light of the Pleiades from a small planet on an autumn evening and standing in that light surrounded by blue-white suns whose radiation you can feel on your face looking back toward a sky where the star you came from is invisible, too far away and too ordinary to find, without instruments lost in the undifferentiated brilliance of a sky full of closer, stranger, more luminous things. The warmth of your home star reaches you now across 8 minutes of space, arriving on a world that has sheltered your species for 300,000 years. It is a specific warmth, familiar in a way that no other light in the cosmos could be. The warmth of origin of belonging of the particular place where consciousness first arrived at the capacity to ask how far it could go. The distance between that warmth and the stars is not a wall, it is a question. And the universe has already provided the answer, written in mathematics, verified by experiment, encoded in the equations of a man who spent his days examining patent applications in a modest building on a cobblestone street in Bern, and his evenings asking what it would look like to ride alongside a beam of light. The answer is far, farther than any distance human experience has yet made real, farther than intuition can follow without the guidance of the equations, farther perhaps than any generation alive today will live to see confirmed, but not infinitely far, not impossibly far, just far enough to require everything.